Hmm. Hmm. No. Okay, I'm not sure how to
I wonder how we'd go about this operation.
effectively does do the thing.
Hup. Hip. Huh. Hum.
Unblocked, distance too far.
Hup. Hip.
Alright, stick with me here. Something huge happened last year that honestly got way underreported. We hit what might just be a critical milestone in one of the most important arms races our species has engaged in for the last half-century. And it all has to do with this compound, zocerebalpin, which is an experimental new antibiotic developed by the Swiss pharma behemoth Roche. Late last year, Roche announced that phase 1 clinical trials testing the safety and efficacy of this new antibiotic were successful enough to push zocerebalpin straight into a stage 3 trial slated for early this year. Even though that's not a guarantee this drug will get approved, phase 3 is still a huge deal considering most new antibiotics barely make it out of the stage 1 and 2 trials. More importantly, this is the first time a new class of antibiotic that can actually kill drug-resistant superbugs has gotten this far in the developmental process in over 50 years. But also, it's the way that zocerebalpin got developed that's the most exciting. The structure of zocerebalpin was refined and built over multiple years with the assistance of an old-school machine learning algorithm. Today, I want to use zocerebalpin and its development story as a lens to show you how quickly the science of biology is accelerating now that we're starting to share more and more of our research burden with computers. Can we use bots to eradicate our worst bugs? Let's find out. And hey, welcome back to Clockwork, a show about the tiny, beautiful molecules at the foundation of everything you do. Make sure you subscribe if you want a better understanding of how your chemistry roots you to the world. And check out our community on Patreon to see our latest sticker packs, temporary tattoos, and papercraft molecules that celebrate your biochemistry. But anyway, we've got a lot of ground to cover here, so let's not waste any time. Starting off with antibiotics in general. Okay, let's rush the basics. For the purposes of this video, an antibiotic is any compound we use to control or kill an infectious bacteria that's making us sick, something pathogenic. This is actually a super hard thing to pull off chemically if you think about it, because for an antibiotic to work, it has to cause significant harm to one living thing while not really affecting the live organism that it's inside of. Since we're all made out of mostly the same chemicals, this amounts to a pretty high-stakes game of spot the difference where we're constantly trying to smash bacterial machines while leaving our own component parts untouched. Penicillin is the classic example here. This beautiful compound with its iconic beta-lactam ring jams up the works in bacterial proteins like this one, which knit a sugary mesh called peptidoglycan. This is kind of like the cell wall of gram-positive bacteria, and when penicillin gets stuck in here and blocks production, these bacteria will end up exploding once they try to grow or divide without enough peptidoglycan for full coverage. Nice. But that's not the kind of pathogen we're trying to treat today. We've got something way worse to deal with. There are also gram-negative bacteria that use less peptidoglycan and instead rely on a second cell membrane on top of the regular one. Getting an antibiotic into these guys is even harder because now you have two membranes plus all the goofy stuff in this periplasm to get through. While we've developed tons of antibiotics to deal with bacteria of all types, we haven't built a new class of antibiotics targeting gram-negative bacteria in 50 years. We've just been iterating and optimizing around the handful of antibiotic genres we already have. And I'll get into why that is a little later, but for now, let's keep unpacking how bad of a problem that is first. With very few new enough weapons in our arsenal, some gram-negative species of bacteria have managed to evolve truly overwhelming antibiotic resistance. Catching these superbugs can become a pretty huge emergency. And one of the true big bads of these overpowered pathogens are these guys, which are carbapenem-resistant strains of a species called Acinetobacter baumannii, or crab for short. And Acinetobacter are a tough opponent to deal with even at the base level. They're ubiquitous, opportunistic little blobs that typically move in and try to cut out a little territory for themselves when a person is already severely ill. They clump together in these very tough biofilms, which are difficult to clean, which allows them to persist on surfaces for weeks while they wait to bump into a new host. Their whole MO is persist and resist. They fortify their double cell wall with this hard-to-penetrate lipopolysaccharide coating. Even worse, that coating will explode off of Acinetobacter individuals if they get engulfed by one of your immune cells as part of a normal immune response. Once inside, those lipopolysaccharides, or LPS for short by the way, turn out to be super toxic to immune cells, killing them and limiting how much of a frontline response you can mount as this bacteria set up shop and entrench themselves. And even worse, if they develop resistance to an antibiotic called carbapenem, that's a whole new world of bad news. Carbapenem is like a streamlined, ultra-efficient penicillin, all the beta-lactam power with no frills. Carbapenem is reserved as a last-line antibiotic for severe infections, but since Acinetobacter baumannii populations can persist so well, that means that crab strains tend to accumulate in places where there are lots of sick sick people, like hospitals. It's extremely difficult to treat a crab infection, and they tend to cause sepsis and severe pneumonia. With treatment options so limited, crab strains boast a 40 to 60% death rate once they establish an infection. Globally, crab-specific strains account for a little over 50,000 deaths per year, but they also incur a significant clinical burden, and the big concern is that death toll can skyrocket as resistance spreads. So yeah, these guys are a priority 1 global health emergency, top of the WHO's most wanted list. And this is why it's so huge that zocerabulpin made it this far into clinical trials. This drug has the potential to be a beast. But before we get into why, let's hear a quick message from this video's sponsor, which is, spoiler alert, me again. This episode of Clockwork is brought to you by our incredible supporters at patreon.com/clockworkshow. Making these animations is incredibly labor-intensive and time-consuming, but our Patreon subscribers empower this channel to explore topics that serve our understanding of the science instead of just serving the algorithm. Subscribers also get real perks like our monthly sticker club and papercraft series. We're building a lot of cool things over at patreon.com/clockworkshow. If you like these videos and want to be a part of what makes them possible, check us out and subscribe today. For now, let's get back to the video. So zocerabulpin is a huge deal for 2 main reasons, that being how it works and how it was developed. I'm a molecular biology sicko at heart, so let's dive into how zocerabulpin kills these crab fellas first. And right off the bat, do you notice anything about zocerabulpin that stands out compared to the other antibiotics I've shown so far? I mean, antibiotics are a pretty broad category from the jump, and I haven't shown you anything super comprehensive. But honestly, penicillin is a better representative of the average antibiotic, weighing in at about 330 daltons, with a dalton basically being just a count of the number of protons and neutrons in a molecule. Most antibiotics in the real world that have real clinical use weigh in at around 400 daltons, with the vast majority of them keeping things under 600. But zocerabulpin is a beast by comparison, weighing in at a few atoms shy of 800 daltons. With that size alone, it's incredible that zocerabulpin works at all. But I'll try to cover why when we talk about development. For now, I'm locking in on mechanism. Let's check in on how zocerabulpin solves our little crab problem here. So Acinetobacter is a particularly intense gram-negative fortress to penetrate. Zooming into a single individual, we've got this double-layered membrane, and Acinetobacter is particularly thorny by adding a whole layer of these lipopolysaccharides on the outside. And while this coating gives Acinetobacter an advantage, we're actually going to exploit that when zocerabulpin comes knocking. These lipopolysaccharides are an incredible added defense for Acinetobacter. They help individuals glue themselves together, block most medicines outright, and wreck the immune cells that ingest and destroy infecting Acinetobacter invaders. But because this gunk is so, well, weird, it needs to be actively pushed to the outer membrane of these bacteria. And that's going to be our opening. All across this periplasmic space, you'll find this little protein conveyor belt connecting the 2 membranes. This is the LPT-B2-FGC complex, but for us, let's just call it the LPT conveyor belt. The 2 B subunits down here use ATP energy to push lipopolysaccharides into the central channel, which then moves them up the bridge and onto the outer membrane. Now, people have been trying to target this conveyor belt for ages, and the underlying theory here is that if we can block this conveyor belt, then this LPS goo won't be up top to block other kinds of antibiotics, allowing them to get entry. But one thing I want to point out while we're here, the team that developed zocerabulpin wasn't necessarily trying to target this LPS conveyor belt. More on that down the line, just keep that in the back of your head for now. And even more importantly, we're going to see that we don't necessarily need any other antibiotics to come in once zocerabulpin has broken the LPS train. But you guessed it, I'll explore why in a second. What's important is zocerabulpin is going to act like a kind of molecular glue that will jam up and break this conveyor belt. Here's how. Zocerabulpin can sneak past the LPS barrier and bind right in this pocket as a new lipopolysaccharide is entering. That chemical bond will be so absolute that nothing is going to pry this antibiotic out of this channel, basically welding the LPS to the channel and sealing the whole thing shut. And there's going to be no more lipopolysaccharides making it up through this conveyor belt. We have completely shut down this transportation mechanism. Nice. But that's where it gets interesting, because we don't actually need zocerabulpin as like an opening move that just drops Acinetobacter's shields before we throw out the real fatal blow. This drug by itself kills the bacteria outright, because it turns out these bacteria have a completely separate sensor that tells them when to stop making that LPS coating. When the outer shell is full, excess lipopolysaccharides will overflow and bump into this protein, which turns off the LPS factory inside the bacteria. However, with this conveyor belt turned off, that switch never gets flipped, and these lipopolysaccharides build up down here in the bacterial cytoplasm, organism with no way to get transported out. And you might remember from before how I said this stuff is super toxic to our immune cells. And I mean, yeah, it turns out we're all made out of the same chemicals here, and a high LPS concentration also becomes pretty toxic pretty quick for Acinetobacter. So this LPS will build up enough to poison Acinetobacter individuals to death with their own cell wall coating. Nice. Congrats, crabs, you played yourself. Nice strategy with that goo barrier. Hope you all enjoy the slow creep of metabolic collapse. So, in short, to review, this very large new class of antibiotic wedges itself into this bacteria's goo conveyor, which causes a toxic buildup of lipopolysaccharides to nuke this punk from the inside. Awesome. And while this is all cool and exciting, remember, we're only in Phase 3 trials here. Phase 3 is genuinely a big deal, but it's no guarantee that zosterobalpin will clear the high bar it needs in order to get real-world approval. If it does get approved, though, the papers that announced zosterobalpin and described its mechanism also managed to identify a handful of promising new drug-binding targets, which will allow researchers to expand this new antibiotic category with more compounds that get out ahead of any resistance old Krabby here manages to evolve in the meantime. But that's the gist of the landscape and a high level of the mechanism of how zosterobalpin works. But honestly, that's not the cool part of the story. I mean, it is to me, but whatever. That might not even be the reason you clicked on this video. Sorry for bearing the lead, by the way. The really interesting part here is how zosterobalpin was developed. Like I said at the beginning, our civilization is approaching a potential antibiotic resistance crisis. Bugs like Acinetobacter have been able to evolve crab mode because we just haven't been able to meaningfully expand our antibiotic arsenal in the last few decades. But like, why, though? It has to do with how we've gone about discovering new antibiotic compounds. And I had a whole long bit explaining that scripted in this video, but luckily the good folks at Minute Earth put out a really solid summary of the problem. Y'all should check that video out and head back here if you want a little more context. In short, we've largely developed our antibiotics by hunting down weapons other organisms use to fight bacteria. And it kind of looks like we've run out of air quotes natural antibiotics that we can actually discover and refine for now. More context from Minute Earth, please check them out. Which makes zosterobalpin and its discovery story potentially very valuable, because the research team at Roche that developed this antibiotic did so with the assistance of an old-school machine learning algorithm. And as a non-computer guy, I think I need to make this super clear. This is not generative AI. I'll get to that towards the end of this video. Zosterobalpin was discovered and refined through an old-school random forest machine learning algorithm. Drug discovery can be slow like that, where we're only seeing real results generated from the technology of the late 2010s. But still, how can machine learning basically pull a new drug like zosterobalpin out of the ether? Check this out. Again, zosterobalpin is a massive compound. It's also very hard to pronounce, and I don't think I'm doing it right. And if not, it's open season on me in the comments. I get it. Why did I cover this? Refining something like this structure without at least a template from the natural world would take eons using old-school drug discovery methods. But scientists didn't just pull this from nothing either. Zosterobalpin is something called a tethered macrocyclic peptide. To briefly dip our toes into the deep chemistry here, macrocyclic peptides have been a big research focus for the past 20 years or so, especially in big pharma and the biotech scene. You basically take a chain of amino acids like any protein and then tether the ends together in a big old circle. The hope has been that we can use the diversity inherent in this kind of structure to build drugs with the specificity of things like monoclonal antibodies, which are gigantic, but with the deliverability of a much more compact small molecule drug, think penicillin. Pulling this off and then developing a platform that allows you to build specific use MCPs would be kind of like a mid-tier holy grail in the pharma world. Kinda. At least that's what the press releases make it sound like. Now, some macrocyclic peptides managed to show some antibiotic potential in the past, but since we're talking about peptides here, theoretically you can mix and match any number of amino acid links into a circular chain like this, meaning there are billions of potential macrocyclic peptides we could synthesize. And that's why we need to deploy computers, because Roche took the shotgun approach to try and find useful variants of a macrocyclic peptide, using a method called whole-cell phenotypic screening. It works like this. Roche paid a biotech firm to synthesize a whole bunch of different kinds of macrocyclic peptides. Just shy of 45,000 unique compounds. They then took those tethered macrocyclic peptides and tested those against a bunch of different strains of bacteria. Just that step alone produced, you guessed it, a whole mountain of data to sift through. And this is where machine learning comes in. Building off of a framework developed by a team at UC San Diego back in the day, researchers at Roche scanned every single bacterial strain tested with each one of those compounds compounds and fed those images into a machine learning algorithm that, to oversimplify, categorized how each macrocyclic peptide affected those bacterial cells. That framework from UC San Diego, called cytological profiling, allows folks to identify subtle changes in bacterial structure and metabolism just from these small differences in how these red and blue dyes are processed, which means that teams can filter out less effective compounds real quick. The first round of tests at Roche cut the candidate list down to a single small cluster of similar compounds, with just 4 having the most promise. They further refined these structures by testing which of them would dissolve better in blood plasma, which resulted in what would eventually be the structure of zosterolbalpin. Nice. Nothing like YouTube to synthesize decades of drug research into like half a sentence, right? It's awesome. And yeah, while this section of the video feels like fan posting about a massive pharmaceutical company, it's important to keep in mind that zosterolbalpin is the culmination of tons of diverse research projects from all sorts of different players, with publicly funded traditional research building a foundation that industry players iterated on top of. And that's why this is such an exciting moment in the life sciences. We're seeing a lot of diverse research paths with decades of groundwork starting to cohere in ways that are making the discovery process for lots of different things so much faster. Like, sure, the shotgun method Roche used here works because it's possible to profitably synthesize tens of thousands of different macrocyclic peptides for machine learning assessment, but is it possible to narrow that field before we start building real chemicals in the real world? And you know what? That's going to briefly bring us to the new hotness taking over our economy, generative AI, and specifically for us, generative models for building new antibiotics. I'm going to keep this brief and focus on only one example, but there's a lot of development happening in the life sciences around generative AI. For me personally, general use AI models feel more overhyped than anything, and I haven't found a single way to make AI fit into any of my daily workflows. But models engineered for specific purposes, especially in chemistry, are starting to show a lot of promise. In particular, the James Collins lab out of MIT has been producing genuinely incredible results as they refine their way toward machine learning-powered antibiotic discovery. At around the same time the structure and mechanism for zosterolbalpin was announced, the Collins lab published research tied to an AI model that helped synthesize another entirely new class of antibiotic that showed efficacy against some of the gnarlier strains of Staphylococcus aureus. That was cool, but then a few months back they expanded on that with this monster of a paper outlining a way more intense method for developing new antibiotics. I couldn't be less of a computer guy, so I'm going to boil this down to the most bare-bone details possible. The generative side of this paper comes in 2 parts. First, the team at the Collins lab fed over 45 million possible chemical fragments into a graph neural network that was testing for possible efficacy against Staphylococcus aureus and the bacteria that causes gonorrhea. The results generated from that neural network were then fed into 2 generative algorithms which turned those promising fragments into full synthesizable molecules. Those 2 steps filtered those 45 million fragments down to just 24 potential drug candidates, which the Collins lab then synthesized and tested against live bacteria. This is the key distinction that makes me way more interested in results from generative AI in the life sciences. Once you've AI generated a possible drug candidate or compound or anything, you can just build it in the real world and use the old school scientific method to verify whether it works or not. No hallucinations, no vaporware, actually verifiable results. In real life, 7 of those 24 generated structures showed real world effects on their target bacteria. But this paper goes into way more detail about how 2 of those novel compounds might represent 2 entirely new classes of antibiotic that damage staph and gonorrhea in a unique way. But we have to keep in mind that at best, this is the very first step in a very long process. Like right now, there's not nearly enough data to see if these 2 compounds are actually promising or not. Verifying if a structure actually works as a medicine requires just so much more data before we can start getting excited and talking about clinical trials. And heck, even the way more promising results from zosterolbalpin can get completely derailed during phase 3 trials this year. You rightly have to clear a lot of barriers in order to prove medicine is safe and effective before you start saving the world with a new class of antibiotics. To hammer it home even harder, zosterolbalpin is the culmination of a tech tree that goes all the way back to 2013. None of these AI-generated chemicals are going to be changing the world tomorrow. And I mean, for real, check back with me in a decade to see if these things actually showed real promise, right? And so the point of this video isn't to overhype the promise of AI or be a cheerleader for Big Pharma's complicated role in the broader scientific landscape. Instead, I want you to be excited for what feels like a truly revelatory moment in the history of the life sciences. The last 70 years or so of molecular biology has just been one paradigm shift after another. But the advent of CRISPR and efficient sequencing and new imaging methods have empowered fundamental research teams to make all sorts of incredible leaps in our understanding of the base mechanics of cellular life. life. Of course, those leaps have come with a reckoning that biochemistry operates in ways that are far more complex and inscrutable than we initially predicted. But even if the problems in biology become larger and thornier, our capacity to break those problems down and find solutions that compound on each other appears to be growing at its own exponential rate. As best I can, I want to build a window for you to see all the new wonders coming out of this incredible moment in biology. The next few years are going to be a wild ride as these techniques get more and more refined, and I'm super excited to explore all the twists and turns with you. For now, though, this is just a good start. I really appreciate your time. Thanks for exploring all this with me. And hey, thanks again for making it all the way through this video. If you liked this video, throw us a like and subscribe so you don't miss any future episodes. We're coming out of a pretty tough period here at Clockwork HQ, and I'm hopeful that means we'll be producing videos a lot faster moving forward. Our subscribers at patreon.com/clockworkshow also help us roll with the punches as those issues come up. Consider subscribing to our monthly sticker club or papercraft series to keep these videos for free for everyone forever. At the same time, check us out at watchclockwork.com and sign up for our newsletter. That's another great way to show your support. Otherwise, you've already been a huge help by making it this far into the video. Thank you so much for being here. For now, real quick, just let me know what your favorite planet is in the comments. I just want to see something here. Either way, I really appreciate your time. Thanks so much for being here. As always, I like to leave you with peace, love, and beta-lactam rings. Everyone be well. Thank you so much.
Of course it's going to be blocked. Because the other thing is loaded in.
Hey, do you ever wonder mid-rep how exactly all this works? Like, if your whole body, even your muscles, are made up of just trillions of tiny cells, how do they all work together to lift all this weight? Your strength actually comes down to an incredible kind of modular precision. All of your muscles across your whole body are, in a way, millions and millions of repeats of the same handful of structures. By going down to the molecular level and building up the mechanism of your muscles, protein by protein, you can get an incredible view of the sheer coordination it takes just to keep you up and moving. The gears and levers that make up your muscle fibers trace their history back billions of years, before life was even multicellular. By remixing a few structural proteins and assembling them in just the right way, our cells can accomplish incredible amounts of work with very little input. But let's just get right into it. Crack some creatine and settle in for this one, folks. Let's start exploring the sarcomere. And hey, welcome back to Clockwork, a show about the tiny, beautiful molecules at the foundation of everything you do. Make sure you subscribe if you want a better understanding of how your chemistry roots you to the world. And check out our community on Patreon to see our latest sticker packs, temporary tattoos, and papercraft molecules that celebrate your biochemistry. But anyway, let's get right into how your muscles work. And I'm gonna do the best I can to speedrun through the anatomy to get to the cool stuff at the molecular level. So yeah, the basics. All of our motion is powered by our muscles, whose main job is to contract and get shorter. Every movement comes from muscle tissue pulling on some part of your skeleton, with most muscles coming in pairs so one partner can pull the other one back after a contraction. Moving further down, that contraction requires an incredible amount of coordination to make sure opposing forces don't accidentally rip your cells apart or anything. So muscles are made of very unique cells called myocytes. You normally imagine cells that look like this, right? They're very square or very round, but always like roughly the same length and height. Muscle cells are some of the most specialized tissue known to nature, and they only care about getting shorter and longer. Therefore, these cells are long, thin fibers that are the result of lots of progenitor cells fusing together, which means that one muscle cell actually has several nuclei running the show here in tandem. Underneath the surface, these cells are just bundles of protein fibers called myofibrils, which are surrounded by support structures like transverse tubules and the sarcoplasmic reticulum, with most of the rest of the space in here getting absolutely stuffed with as many mitochondria as possible. You know, to power all the movement that happens in here. But now we're getting to the good stuff. So if we briefly switch to an electron microscope view of these myofibrils, you're going to start understanding what makes these cells so powerful. Each myofibril is incredibly well organized. I mean, look at these bands of protein. They line up almost perfectly across several different myofibrils. That's because each fiber inside every muscle cell is just the same fundamental unit repeated over and over. This region, dark band to light band to dark again, is a single structure called a sarcomere. Across a single muscle, every sarcomere is pretty much exactly the same, but different muscles and muscle types might have slightly different sarcomeres with slightly different sizes. Either way, as your muscles grow, they're basically just stacking up new sarcomeres. So if you learn how one single sarcomere operates, you basically know how the entire muscle works. So if we zoom all the way in, we can finally start exploring the proteins that power all this movement. Behold the sarcomere. Down here at the molecular level, it honestly feels like we're in a dense forest more than anything, with long, thin filaments and elastic connectors towering over us. A sarcomere is three main components repeated over and over again, basically. We've got the thick filaments in red, thin filaments in blue, and then a supporting cast of structural proteins holding everything together. If you want to skip the rest of this video, all you need to know is that the thick filaments power muscle contraction by using all these little heads to grab and pull the thin filaments down like this, thereby making the whole sarcomere contract lengthwise. But come on, how does that even work? Let's keep going. The middle of the sarcomere is, get this, the M band. This is also the dead center of these thick filaments and their mesh of support proteins. Basically, two identical thick filaments sprout out of this spot, facing away from each other, trunk to trunk, butt to butt, soul to soul, whatever you want to say. Moving outwards, we get to the A band, probably the best defined area of the sarcomere, where the thick and thin filaments overlap with each other, and honestly, this is where the magic happens. But hold on, moving a little further out is the I band, which is just the thin filaments and the elastic connector proteins holding everything together, which eventually gives way to another super dense region. Behold, the Z disc, the border between two sarcomeres. Here, a bunch of molecular scaffolding glues the thin filaments of two neighboring sarcomeres together, while providing an anchor for the elastic connectors of both adjacent sarcomeres as well. Now, this whole thing has been a glorified two-dimensional side view. If we look at this thing from the bottom them up, we can see that a bunch of thick and thin filaments are organized around each other in kind of like repeatable layers. Because of how elastic and pliable our muscles have to be, the details here are kind of fuzzy, but at the basic level, these muscle filaments are arranged in this repeating hexagonal pattern. Every thick filament is more or less 45 nanometers away from the thick filament next door, while the thin filaments fill in the gaps. Alright, cool, that's the lay of the land, nice. We've got the shape of things down pretty good, but how does all this work? That's kind of like why we're here, right? And you know what? Surprise, we're actually going to have to go down one more level and break these filaments into their component parts, which is going to tell us everything we need to know about how your muscles contract. But first, a quick word from the advertiser for this video, which is surprise me. Today's episode is brought to you by my supporters over at patreon.com/clockworkshow. We've been developing a new benefit model with physical perks for the last 6 months over there, and the response has just been incredible. If you like videos like this, they really only are possible because of the support I get from my patrons. In return, I'm able to send genuinely beautiful stickers, temporary tattoos, and paper crafts to my audience around the world. It is such a joy to get to make beautiful things for such beautiful people, and these perks are only going to get better in 2026. We're really close to being able to take some really big swings here at Clockwork HQ, and it would mean the world to me if you checked us out over there. Folks who join us at patreon.com/clockworkshow by clicking the link in the description will get last month's perks as a free bonus, so you can have all these amazing Sarcomere stickers and paper crafts on top of watching this video. If you thought about joining us before, now really is the time as we enter into a make or break period here at Clockwork HQ. But anyway, let's get back to building this sarcomere. Here we are, where we can finally unpack the mechanics of how sarcomeres work. Again, at a high level, these structures contract when the myosin heads on the thick filament pull the thin filament toward the M line. This system has been fine-tuned over the last billion years or so. I mean, both actin and myosin are ancient proteins that go back to the dawn of eukaryotic life and our days as single-celled blobs floating around the ocean. And coming up, we're going to see how these individual proteins create an incredible system for so much motion. So let's break it down. First up is the thin filaments. They basically hold the whole sarcomere together and are like the medium that's being contracted throughout your muscles. The star of the show here is in blue. It's the versatile actin protein that's pretty much ubiquitous across all life. Actin is a wonder. Your cells are constantly pumping out these little subunits, and when activated, they can spontaneously polymerize into these cool little filaments. And even cooler, they can also spontaneously depolymerize on the back end as well. As the title implies, actin is from your cytoskeleton, so it's going to provide some structure and some rigidity throughout your cells, but your body also uses actin's ability to polymerize and depolymerize on demand as a way for folks like your white blood cells to move around. And I mean, look at them go, right? All those little, like, tentacles, right? They're probably membrane protrusions being driven by actin polymerization. This stuff is incredibly fast, but the role actin has in muscles is a little different. We want our actin here to stick around and polymerize in the right way at the exact right length and not fall apart at random. So your muscle cells are going to build some support structures around actin to make it a filament and not something super dynamic that breaks apart too much. First up, your muscle cells build this little yardstick called nebulin. Nebulin doesn't look like much, but it's one of the single largest proteins your body builds on a regular basis. And if that makes you ask what the biggest one is, sit tight, that's coming up in like seconds, right? Nebulin's job is to act as a scaffold for actin to polymerize around. Instead of letting actin get all dynamic and depolymerize on a whim, nebulin stabilizes actin in its filament form, keeping your muscles from breaking apart for no reason. This gives nebulin the power to determine sarcomere length, but more on that towards the end of the video, actually. And the thin filament is further stabilized by this coil, tropomyosin. And sure enough, tropomyosin also has a really important job outside of stability, working in tandem with this last protein called troponin. But let's build the rest of this sarcomere before we get ahead of ourselves. Before we head down to the thick filament and the main event of this video, really, I may as well mention what is objectively the coolest protein in your muscles, since it's also up here anyway. These cables are copies of the same protein, titin, which is incredible in its sheer mass. What you're seeing right now is actually 3 copies of titin that surround a single thick filament. A single titin chain is one singular protein coded for by the single longest gene in your DNA. Titin in our muscle cells is 34,300-ish amino acids long, just incredibly massive. By comparison, a more average protein like hemoglobin is only about 550 amino acids when you add up all the subunits together. So we are on just an incredible incredibly massive scale. And you know what, quick tangent, I was gonna make a whole thing out of the fact that Titan is the largest peptide node to science, and how cool that is that it's, invertebrate muscles, but then 2 years back, this team out of the Scripps Institute in San Diego ruined the fun by uncovering an even more massive protein, PKZilla, that's 30% more massive than Titan while also somehow being cooler, and uses all that unmodelable heft to help this one algae build this really intense looking toxin or whatever. I mean, honestly, that just kind of feels like its own video though. But anyway, don't let Titan's outsized reputation intimidate you. This structure is manageable once you peek under the hood, because instead of being like 34,000 distinct little puzzle pieces making up this cable, it's basically just the same 3 protein domains repeated a bunch of times. And to be even more real with you, it's just these immunoglobulin and fibronectin domains that get copy-pasted like a few hundred times while Titan is synthesized. The fibronectin domains provide rigidity and structure, while up in the I-band, these immunoglobulin units fold and unfold, allowing Titan to act kind of like a molecular spring, absorbing some of the tension and force from the stress of contraction. Titan spans the whole length of the sarcomere, with a single Titan cable anchored to the M-line and Z-disc. The tension and elasticity that Titan brings to the table helps hold the sarcomere together, and that spring action allows Titan to help pull the sarcomere back to the relaxed state after muscle contraction, which gives our motion a ton more power and flexibility compared to folks like insects and other critters who lack Titan in their muscles. But getting back down to the biochem real quick, what's cool is that these links actually provide elasticity in a few different ways. First up, the actual individual links in these chains will bend together a little like this when your muscles are relaxed, and then these kinks will straighten out as your muscle contracts more and more. And this is where it gets wild, because according to certain models, some of these immunoglobulin domains can unfold completely into a straight line when the cable is under enough tension, which makes Titan even springier. Our bodies can use these different levels of elasticity to accomplish so much extra work, but I'll need to save those for a part 2 where we improve this sarcomere model with better simulations of how Titan works. Make sure you comment if that deep level of biophysics is something you actually want to see. I mean, that's the only way I'll be able to put myself through the pain of that level of modeling. Anyway though, for now, just remember that Titan is a long elastic cable that has a couple of distinct regions where these immunoglobulin and fibronectin domains will repeat in a certain pattern. That's going to be important to have in mind when we round things out by making it all the way down to the thick filament. Which, speaking of which, let's just get down there now. The myosin filament. Finally, we're getting to the meat of this thing. The core of your muscles are built
Burn there, I think.
around these thick filaments, which mainly are a rotating stack of these long myosin molecules. Our muscular myosins come in pairs with long, winding tails that wrap around each other, which are both capped off by a motor domain attached to a flexible neck. These myosin domains kind of helically stack on top of each other, which is how we build our thick filament. The average myosin filament is going to have around 294 of these myosin molecules stacked on top of each other, with 2 kind of identical copies branching out trunk to trunk from the M line. There's one last super cool detail about how this all comes together, but I'm going to save that for the end. For now, let's get to the main event. Let's see how these myosin motors pull on the actins inside that thin filament. And to do this, let's get out of this big simulation and zoom in on the interaction between one myosin and a nearby thin filament. What we're about to see is the power stroke cycle for these myosin motors. Stick with me here, we're just going to level up through it. Ready? So how exactly does myosin bind and move these long, thin filaments? As always, it comes down to one of the most important maxims in all biology: structure equals function. And myosin is able to pull on actin thanks to a repeated sequence of very subtle shape changes that are powered by everyone's favorite energy currency, adenosine triphosphate, or ATP. And you know what? We're just going to start at the very end of the last power stroke. Myosin has just finished pulling this actin molecule up a little bit, but it's still bonded to this actin unit. We really don't want to stay stuck like this for long because we don't want to jam up the rest of the sarcomere as the muscle continues to contract. Luckily, the mitochondria that are crammed up against these sarcomeres are just flooding this area with ATP, which means a fresh energetic molecule of the stuff is going to quickly find and bind with the little pocket on the back of our spent myosin right here. And this is one of the magic pieces of biochemistry. Almost every single thing that happens to any protein is going to change its shape a little bit. That's how dynamic things are down here. And therefore, even the little nudge from this ATP is going to change the shape of our myosin head just subtly enough to help it dislodge from this actin filament, freeing it up to start the next power stroke cycle. And this is the cool part that makes the power stroke so automatic and so fast. Letting go of this actin is going to release a little tension inside this motor. This conformation is perfectly primed to hydrolyze this ATP. This terminal phosphate group at the end will pop off, which, to oversimplify, releases a burst of energy that the surrounding myosin motor domain can use to change shape. And myosin can only move one way when charged by an ATP burst like this. That energy will throw myosin's lever arm into the primed position. That burst of energy is going to cock the myosin domain back down to the prime state, readying it to grab onto the next actin molecule down the chain. And this brings us to the real magic of myosin and the secret sauce that makes your muscles work. You hear about ATP in biology all the time. ATP is constantly moving energy around your cells by getting hydrolyzed, popping this phosphate group off and releasing that burst of energy. For a lot of proteins, ATP slots into a binding pocket like the one inside myosin right here, transfers its energy, and is then immediately released. But in myosin, when ATP cocks the motor back, it actually gets stuck in the binding pocket here. Sure, this myosin head is now under a lot of tension, but that tension can't get released because this adenosine diphosphate, ADP, and the phosphate it just released are jamming the works up in here. Maybe this sounds clumsy, but it's a brilliant way to make sure that these myosins don't burn through cellular energy for no reason. Instead, think of this like, I don't know, a mousetrap. We're effectively storing the energy from ATP until the exact moment we need it, which is when this myosin comes in actual physical contact with an actin. And there's a great binding spot for myosin in this groove on actin right here, and attaching to that actin will change the motor domain's head just enough to pop out this little phosphate, which again allows all that tension to kick the myosin lever arm here down, which for physics reasons is going to actually shove the motor and actin up, which is the actual power stroke of this cycle. As soon as the power stroke here finishes, a new ATP can slot in and free myosin from its bonds to actin and start the cycle all over again. And this system by itself is incredibly powerful and beyond versatile. This automatic interaction between actin and myosin powers cellular shape changes, cell division, some motor proteins, and a whole host of other jobs all throughout the whole eukaryotic domain. Now yes, this is complicated, but the complexity here allows for one last incredible layer of control. Because if binding to actin automatically activates these myosin motors, and, actin is kept within binding distance of myosin basically at all times in these near crystalline sarcomeres, then, how do our cells keep myosin from just power stroking all the time? I kind of wish I had reworded that, but I'm in too deep now, so let's just keep going. Because this is the best part of the video. This rocks. We get to put the whole thing together now. Let's focus back on the thin filament and check in on the last piece of this puzzle. Remember, our thin filaments aren't just raw actin here. They're stabilized by these winding coils of tropomyosin. Actually, coiled coils of tropomyosin, but whatever. And those coils are occasionally studded with these troponin complexes we glossed over earlier. Now, troponin controls the real magic of the sarcomere, and here's how. Turns out, tropomyosin isn't just stabilizing our thin filaments, it's also actively blocking the part of the actin molecule that myosin can bind to. During an activity, these myosin motors are just endlessly teased, forever caught in that post-ATP tension with nowhere to bind. All tension, no release, until you actually decide it's time to flex something. When it's actually time for a muscle to contract, your nervous system is going to send an impulse directly to that muscle. That nerve contact is directly connected to all those little tubes that surround the myofibrils we discussed earlier. And once that signal arrives, the sarcoplasmic reticulum here turns on the pumps and floods the myofibril with calcium ions. Once inside the sarcomeric space, that calcium will bind to troponin, which will activate and change its shape pretty sharply. That shape change is going to pull tropomyosin away from actin's binding cleft, allowing myosin to actually contact the filament and roll through the power stroke cycle. Meanwhile, at the exact same time, there are pumps between the sarcomere and the sarcoplasmic reticulum that are constantly pumping calcium out of the myofibril, which keep the, contract signal short and to the point. But yeah, that's the main gist of it. Vertebrates like us have re-engineered cytoskeletal proteins to massively increase the amount of leverage we have over the outside world. For me, the most important thing that allows this to work is how perfectly organized these sarcomeres are. Don't forget how they line up so well to ensure that all these little proteins end up all working in the same direction. How do we even pull that off when living structures can look so messy in other ways? And this is actually another one of the superpowers of Titan. Remember how Titan is just 3 different subunits repeated over and over in different patterns. Down here in the thick filament, Titan just repeats these immunoglobulin and fibronectin domains in an 11-unit pattern over and over again. And this 11
come on. Why do you have that? Valhalla.
Unit pattern actually repeats 11 times. Nice. This is the C-type super repeat, and evidence suggests that this acts like a molecular ruler, giving the tails of these big ol' myosin molecules a place to start binding. Once that first myosin molecule slots in on this first super repeat from Titan, the rest of the myosins can slot into place, stacking up helically like this, all 294 of them stacked helically on top of each other, and the rest of the filaments fall into line all around it. With Titan and Nebulin, we added a few extra yardsticks and controls, and that's going to help the fuzzy process of cellular life achieve a kind of incredible rigidity and specificity. For me, it's incredible how all this comes together. I love so much how our cellular structures have relatively simple rules that build to fabulous complexity. And like I said at the very beginning, this system is also incredibly modular. By organizing the sarcomere around yardsticks like Nebulin and Titan, our cells can make incredibly different muscle types out of pretty much the same molecular ingredients. If you've seen my big ol' video on how DNA gets transcribed into RNA, you know that one of our secret superpowers is RNA splicing. This big complex called the spliceosome modifies RNA as it gets transcribed from DNA, allowing us to produce tons of different proteins from a single DNA sequence. Alternate splicing of Nebulin and Titan changes the length of these yardsticks and therefore the length of the entire sarcomere. Different lengths and a few other modifications allow for a breathtaking variety in muscle types and jobs. A little added complexity yields an astonishing amount of extra control. And gosh, we are able to do just so much with our own internal variety. That's the main thing I always want you to take away from videos like this. Together, we slog through a whole mess of dense information, and in the end, we're able to put things all together and see the majesty in our biochemical foundations. Frankly, muscle cells are great in that these sarcomeres are organized enough that it's easier for me to show you just how jam-packed our cells are with proteins and structure. It's crowded in these cells, and we're able to do just so much with all these little puzzle pieces. And there's so much more to explore in these sarcomeres, but here's a good place to end this first video. Make sure you hit that comment section if you want to dive even deeper into this particular aspect of chemistry. For now though, I really appreciate your time. Thank you so much for watching. And hey, thanks so much for getting all the way to the end of this video. If you liked this video, make sure you like and subscribe so you don't miss future editions of this series on muscle structure. At the same time, it would mean the world to me if you checked out what we've got cooking over at patreon.com/clockworkshow. This year has a lot of great perks in the works, and I think you're gonna really like it over there. And one bit of housekeeping, I just want y'all to keep in mind that so much got left on the cutting room floor here too. I didn't get to talk about creatine or low duty ratios or anything cool like that. So make sure you let me know if that's something you'll really want to see. Otherwise, the main thing I want you to know is how much it helps me when you make it all the way through a video like this. Just the act of you hearing these words right now effectively is carrying this channel. Thank you so much for being here. But that's a solid place to end things. Let me know what your favorite color is in the comments if you made it this far. For now though, I just really appreciate your time. And as always, I like to leave you with peace, love, and as many C-type super repeats as possible. Everyone be well. Thank you so much.
Endman.
Weapon suite.
Going in.
chapters to start. First up, this video is going to cover Chapter 1, the transcription of DNA into mRNA. Chapter 2 is going to cover translation, or how your cells turn RNA into protein. And this episode is going to come in basically 4 main parts. First up, we're going to have to do a quick overview of the central dogma itself, just to understand the lay of the land for the rest of this series. Next up, we're going to have to talk about our 2 main molecular characters, that's DNA and RNA, and then we'll finally get into the actual act of transcription itself for the bulk of this video. And in part 4, we'll see how that RNA is edited after transcription happened, before it's sent out to do real work in your cellular machinery. Sound good? Let's go. Starting, of course, with what exactly is the central dogma? And I mean, it's hard to distill this down into a sentence. One way to think about it is that the central dogma is the story at the center of all biology. It's a topic around which everything else rotates. At least it was. It's maybe diminished a little bit in importance in the last 30 years or so. And this whole series is aimed at helping you unpack those complications and get a true, rich view of what the central dogma actually is. But in short, the central dogma is how information flows through your cells. In every single one of your cells, you have DNA, a complete archive of all of the genetic information you have from both of your parents. That DNA encodes information in the form of genes. When you need to do anything, your body reads your DNA to transcribe it into RNA. That RNA is then translated into
Произвольная. Произвольная. Там очень много видео на канале. Я тебе могу просто скинуть канал, и ты посмотришь по названиям. Выбери сама, которую ты захочешь посмотреть.
Ну, мы с тобой вместе. Давай что-нибудь вместе.
Не прямо сейчас.
Так, ты знаешь, Яблоко, морковку будешь?
protein. And those proteins, are the actual workers that go on to do the actual business of being you. So, at its simplest form, the information flow in your body is DNA becomes RNA becomes protein, right? Cool. That's the whole business of being alive, at least at a really high level. This series is going to show the central dogma in all its complexity in eukaryotic cells, going well beyond this simple chart. Eventually, we'll loop this chart back around and discover how proteins in our cells talk back to our DNA. And along the way, we're going to shake up this rigid view of how our cells work. Based on how you learn about the central dogma in school, you might think of a cell as a very mechanical robot. What you're going to see starting in this video is how remarkable
Оказывается, уже это...
Ну, сегодня еще можно съесть, но такой достаточно... Он у тебя есть там? У тебя вообще...
remarkably fluid this process is, and that's the most important thing to keep in mind. Living systems are incredibly malleable, and to be clear, we're going to explore the central dogma in your cells specifically. As a card-carrying member of Team Eukaryote, you've got way more complex machine code than the bacterial systems most folks tend to learn about in regular school. Buckle up, because we're not pulling any punches when it comes to trying to understand the complexity at play here. And if you power through some of the incredible complexity we're about to deal with, you'll see how all your complications here aggregate to be kind of a superpower. And let me get you in the mindset for that first. Quick question. If every single one of your cells has a full copy of all of your DNA, then how does a cell in your kidney know to only transcribe and use kidney-related genes? What's stopping individual cells from making the, wrong proteins? Don't answer that now, just think about how that could be managed. But back to the matter at hand. I want to zoom in on this original central dogma chart here to see the full scope of our video. Today we're going on what seems to be a very simple journey. We're going from DNA to RNA. Specifically, we're going to be ending at a specialized kind of RNA called mRNA, or messenger RNA. However long that takes, mRNA is our end destination. If you watched episode 0 of this series, you know just about everything you need to about DNA for this video. Go watch that if you haven't. We'll wait. And hey, welcome back. Let's get to know our other main character before we kick off the real action here. Meet RNA, ribonucleic acid. Like DNA, RNA is a string of little nucleotide letters. The big difference you can see right up front is that RNA only has one strand. The double-stranded structure of DNA rocks for its function. Those two strands make DNA incredibly stable and very easy to copy, which is effectively DNA's main job. Don't break, get copied, be ready to be transcribed. Done. Nice. Meanwhile, the single strand of RNA makes it way more dynamic and also way more fragile. RNA is a molecule of action. The flexibility of RNA allows it to do some genuinely wild things, some of which we'll actually see in this video, others will have to wait for future iterations of this playlist. And you might also notice that the colors are kinda off here too. That's because RNA doesn't use the letter thymine. RNA has its own imposter thymine called uracil. It lines up with adenine just fine during transcription, and that's all that really matters, at least for this video. And for the sake of contrast, contrast, from here on out, I'll be using orange as our primary color for RNA. I think it's important we make our main character stand out for what's to come. Like I said, RNA comes in all sorts of shapes and sizes, but today we're focusing on the vanilla version of your RNA, messenger RNA. mRNA carries the information stored in your genes out into the cell to code for proteins, but getting there is going to be a whole thing. So, to make our view of the central dogma more accurate, this chart should actually read DNA becomes mRNA becomes protein. But like, how exactly does DNA get turned into mRNA? Which brings us to part 2, actual transcription, turning DNA into mRNA. Again, it's not the DNA itself getting converted, it's the information the DNA encodes for. This whole thing goes down in the same place where your DNA lives and gets copied. We're here in the nucleus of, you know what, literally any one of your trillions of cells at any given microsecond. The nucleus here is a big old ball of DNA bundled into these thick chromatin fibers. If we're going to turn DNA into RNA, we're going to have to find a way to stick this complex, RNA polymerase II, onto our DNA. Pol2 here is one of your primary molecular workers, and it is constantly, tirelessly assembling new strips of RNA as your cells need. During this process, RNA polymerase II is going to get loaded onto this DNA strand, and then a bunch of extra workers are going to open this DNA up and allow RNA polymerase II to read that DNA. The reading process is simple enough. This strand up top is what we're actually copying. Keep in mind the DNA's superpower is that it can be copied. Since these DNA bases have a complementary base pair that they can bind with, and since uracil can bind to thymine just fine, RNA polymerase II can use this DNA as a template to synthesize a complementary mRNA molecule. Once transcription gets kicked off, basically new RNA letters are going to come into RNA polymerase II's active site, line up with their complementary base pair, and bind to the growing backbone of our mRNA transcript. So we're not literally converting DNA into RNA. This DNA is being used as a template to assemble an RNA molecule. Awesome. Here's the thing though, RNA polymerase II is just a printer. It doesn't have any knowledge of what action your body needs to take at any given moment. It just needs to get attached to this DNA strand, activated, and freed to print. Meanwhile, the nucleus of your cells isn't just like empty space full of DNA and whatever else. It's chock full of raw DNA and RNA letters floating around in space, just waiting to get added to a new strand. And again, going back to that DNA video, you'll also know that the act of adding a new letter to this transcription actually releases a ton of energy, which means that when you add a new letter to this RNA code, it releases a ton of energy, pushing the transcription machinery along with ease. If you don't manage RNA polymerase II, it'll just sprint down this DNA strand Saquon Barkley style, unstoppable because of how much energy is released in this process. And if that happens, that's not a useful transcript. So in reality, instead of just being this simple printing process, transcription for you is an RNA polymerase management problem way more than anything else. Instead of starting with RNA polymerase II, we're going to meet a whole cast of characters that make sure transcription is on the right track. We're not going to meet all of the protein workers that manage transcription today, just enough of them to get us all the way from a random exposed DNA strand to a completed mRNA transcript. As we get further and further into this playlist, we'll fill in more and more details and see just how many managers there are, but I want to make sure we get a complete story here so we don't get overwhelmed from the very beginning. And if you want to get a better understanding of just how complex this management problem is, I really recommend you check out this video's Clockwork Book Club entry, How Life Works by Philip Ball. Ball has pulled off an incredible achievement with this book, distilling decades of research into a solid page-turner that explains our new understanding of all of the details surrounding the central dogma of biology. A lot of how I'm framing this series will heavily reference this book, so you may as well check it out now if you want to get an idea of where I'm going with this series. How Life Works gets an easy 5 clocks out of 5. I wish Philip Ball was my boss and/or academic advisor, but I'll just be satisfied with hawking his books for now. Back to the video at hand though, let's actually transcribe this DNA segment. Here are the steps we're going to go through. Transcription comes in 5 not at all easy parts. We got pre-initiation, initiation, pausing, elongation, and eventually termination. Each one of these steps has up to dozens of molecular assistants, so get ready for a whole bunch of names, folks. This is going to be a party. Let's go ahead and light this candle. For this video, we've actually kind of skipped the first couple of steps here. Before DNA can ever actually get transcribed, individual DNA strands have to be loosened from their tightly packed chromatin form. We're going to cover how this goes down towards the end of this series because it makes a lot more sense once we've covered the actual basics of RNA transcription and protein translation. For now, let's put in the work to turn this DNA into messenger RNA. And let's get a quick lay of the land as we kick things off. Just to orient ourselves, we're going to travel this way when we start transcribing our DNA strand. Just like replicating DNA, we have to crack open this helix and move across these letters in order to build our RNA chain. chain. Which brings us back to the setup. This gene is exposed and ready for something to bind to it. We're going to kick it off here. It's transcription phase 1, initiation. This gene isn't super special, and has some of the basic features most genes do. The actual coding DNA of this gene is more down here, moving off to the right. Upstream a bit is this region, where a bunch of thymine and adenine letters repeat a bunch. This is your Tata box, folks. It's one of the best named structures in all of biology. Oh, and wait, yeah, that's backwards. So if I flip this around, yes, now you see Tata box, right? Okay, let's rotate back so we keep the same orientation the rest of this video is going to be in. Savor a beautiful label like this while you can, because it's about to get immediately buried. Repeated DNA letters like this are just catnip for specialized proteins that can bind to DNA. Here comes one right now, the instigator for everything that's about to come. This little butterfly-looking fella is, get this, the Tata binding protein. He's actually a smaller subunit of this beefy complex, General Transcription Factor 2D, or just TF2D. Get ready for a lot of acronyms that sound just like this. So 2D is really here to kick things off. 2D's entire job is to first stabilize this DNA strand and get it so that the Tata binding protein actually has a chance to bind to the Tata box. First, the front end of 2D is going to recognize a point just a little downstream of the Tata box, associate there, and then rearrange itself wildly to attach this yellow Tata binding protein. And flipping the view real fast, TPB will lock onto your Tata box and be used as the initial anchor for the scaffolding your cell needs to attach RNA polymerase II to this DNA. As 2D locks in place using the Tata box, it's formed a foundation we can build the rest of the pre-initiation complex on. Another anchoring factor, 2A, is also joining the party right here. 2D has now set enough of a stage for our main character to take their place. RNA polymerase II is going to slot in right here, while a new complex, TF2E, binds, which is going to make way for the rest of the party to start. For the most part, this is your pre-initiation complex, the first major complex built by your transcription team, which means we're ready to go, right? Wrong. With the pre-initiation scaffolding fully assembled, our workers will rearrange a little while the final two elements slot in. At the same time this complex assembles, this massive unit up here is getting recruited as well. This is your mediator. Our mediator complex is here to make sure that it's actually 100% time to turn this DNA into action. This Tata box might have been exposed randomly thanks to, any number of factors. So our cells have another layer of regulatory control built in here. Basically, proteins will bind to DNA segments called enhancers way upstream of the actual gene that needs to be transcribed if it's actually go time. Through a mechanism that scientists are still trying to nail down perfectly, those enhancer elements bind to this mediator. If our mediator gets the correct signals from these enhancers, it will help organize the final steps of the pre-initiation complex assembly. Basically, the mediator is going to help another transcription factor, 2H, into the exact correct position so it can help activate this whole process. It's going to do this by binding to one of the most important and weirdest parts of RNA polymerase II. This long, wiggly string at the end of pol 2 is the enzyme C-terminal domain. This is, in a way, pol 2 is like control rod. And hold up, just a couple of caveats here. This is just a small segment of this C-terminal domain. RNA polymerase II's C-terminal domain is an incredible central platform for transcription. What you're looking at is a very small section of this long thread-like appendage on RNA polymerase. This, control noodle is made up of 52 repeating amino acid sequences. I'm only able to render about 4 of them, so basically 90% of the structure is just not visible in this video. The CTD's job is to get phosphorylated, basically to have phosphate groups added all across the serine amino acids along this structure. During this whole process, as different regulators are needed, this C-terminal domain have different segments get phosphorylated. Meanwhile, the CTD is so long that it can actually act as a holding scaffold for regulators to attach to as they wait their turn to affect the transcription process. Just know that each step of transcription changes the phosphorylation setup in a subtle way. And that's what makes the mediator important. It looks like the mediator's job is it will hold on to the C-terminal domain in a way that TF2H can kick off the first wave of phosphorylation and activate transcription. Let's zoom in to the actual DNA side of this process. 2H here is going to help unwind our DNA strand and properly spool it into the active site of RNA polymerase II, basically just by shoving it backwards. We're now in the open state of this pre-initiation complex. Once it does, all bets are off. This complex is now fully activated, and the energy from adding new letters to that RNA chain will start moving the core transcription machinery rapidly. Which means now that we've met all these characters, we're going to instantly leave them all behind. Nice. And yeah, we're on our way. With RNA polymerase 2 released, initiation is over, and we're ready to jump into the next phase of transcription. But before we do that, let's check in with the sponsor of today's video. Today's video is brought to you by Brilliant, where you learn by doing. For me, I love learning by consistently incrementing my way through a topic. Even something as immense as transcription is learnable as long as you tackle it in bite-sized chunks. That's what makes Brilliant great. It's a learning service with in-depth and incredible lessons that can gradually level up your understanding of the harder sciences. I've been having a great time going through Brilliant lessons on computer science, shoring up my foundations. Each Brilliant lesson is filled with hands-on problem solving that allows you to actually play with concepts. This is a method proven to be 6 times more effective than watching lecture videos. So, while you're establishing a real basis of real knowledge on specific topics, it also helps you work those cognitive processes to help you become a better thinker overall. More importantly, Brilliant is an incremental platform which will help you develop a powerful daily learning habit. You're not going to learn data science or calculus in a single day, but you can incrementally chip away at the foundations of these problems until you can wrestle with the more advanced concepts. If you want to try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/clockwork or scan the QR code on screen. Or you can click the link in the description. You'll also get 20% off of an annual premium subscription. Give them a shot. You genuinely won't be disappointed. But for now, let's go ahead and get back into the video at hand. RNA polymerase 2 has been released, so what happens immediately after that? Turns out it almost immediately gets stopped the second after it started. Awesome. And hey, we've come to the surprise third stage of transcription, pausing. Brought to you by this charming fella, NELF, the negative elongation factor. As this little baby RNA strand finally starts poking its little head out of the core RNA polymerase, for now, it's actually very important to pause here because we need to process this RNA before it gets too long. A single strand makes RNA versatile, but also fragile. Our mRNA here is also getting ready to be shipped into the cytoplasm of our cell proper, where it can get blasted apart by all sorts of intracellular goings-on. So we have to immediately start packing this RNA to ensure some stability here. NELF is here to tackle POL2 long enough so that these yellow RNA capping enzymes can add this little methylated cap on the front of our growing mRNA. This cap is going to keep our little messenger stable, and more importantly, this is also something that our cells use as a kind of ID tag. mRNA is the machine code of the cell, no matter what. If an mRNA strand is loose in the guts of one of your cells, it's going to run into an army of ribosomes and then get translated. Therefore, your cell has a ton of internal defense systems to attack and destroy foreign-looking mRNA. And all this little cap does is block the RNA chewing machinery from accessing the rest of this chain. So honestly, it's a good thing that this is the very first modification we get hit with. So this immediate pause and arrest is just built in to guarantee that we don't run away polymerizing an mRNA molecule that will just get chomped up by your cell's defenses once it gets shipped out. Awesome. With the cap on, our capping enzymes are going to move on to the next baby RNA they need to process. Now, sometimes transcription will just stop here if your cell isn't super ready to make whatever protein this region codes for. NELF down here is actively holding on to the complex, so there's this tension building inside the stalled polymerase that could kick the whole complex off our DNA and kill transcription before it even begins. Unless this really is DNA our cell has tagged for transcription. Let's pan downstream a little bit, where we can see one of the histones that pack DNA into tight little bundles. When we definitely 100% want to transcribe something into protein, these histones will be tagged and altered, allowing this tiny little worker, PTEF-B, to bind. These histones usually are pretty close to where our initial stall happens, so sure enough, PTEF-B is going to be able to hop off this histone and bind to our stalled transcription complex with NELF. PTEF-B will use this scaffold to drop its own phosphorylation onto polymerase 2's controlled stick, and that's going to change all these shapes just enough for POL2 to kick NELF to the curb and finally, truly, get this transcription party going in full swing. Welcome to the next phase of transcription, elongation. PTEF-B has changed things here enough that a massive new cast of helpers can join POL2 and stabilize things enough to get us through most of transcription. Every one of these blue workers is here to either stabilize our growing mRNA or to help unwind the histones that store our DNA. Let's go ahead and see how that works. And you know what? It only took us most of this video, but this is what the majority of transcription looks like. But yeah, let's just take a breather and allow elongation to play out for a sec. We really had to fight our way through a whole army of regulators just to get here, didn't we? Again, talking about the regulation of RNA polymerase II is so much more important than just the basics of transcription itself. So many of the fuzzy details that make us so rich and adaptable live in these dozens and dozens of regulators that keep our cellular machinery on the right track. And I really want to make it clear that I'm barely scratching the surface here in terms of all the assistant proteins that could be deployed to every possible interaction of transcription initiation and transcription elongation. I'm showing you an incredibly narrow, yet complete from start to finish instance of transcription. The goal of this playlist is to help you stand on a complete foundation and then fill in more and more detail, revisiting every facet of the central dogma. The complexity really is the point here. And now we have an excellent jumping off point to explore so many vital cellular processes moving forward. But look at that. We've passed into the 3' untranslated region. Our gene technically is done being transcribed. We're not making any usable code anymore. Let's lock in for the final phase of transcription, termination. RNA polymerase II has crossed out from the coding region of this DNA and has hit the end signal. We are now in the 3' untranslated region. As we pass into the untranslated region, all the lovely elongation factors here are just going to break off from pole 2. Maybe not this dramatically, but, work with me here. At the end of every protein coding gene, there's this little DNA sequence that's here to stop everything. Behold, the polyadenylation signal. The polyadenylation signal is absolute catnip for regulatory proteins. Specifically, a group of workers led by CPSF will bind here, cut our raw RNA at that polyadenylation signal, and help ship this transcript off for final processing. Once our fresh transcript has been snipped off, we're kind of in trouble. Again, RNA polymerase II does not know that transcription is over. It's just a printer. Polymerase is just gonna polymerize, so it'll keep going as long as it's allowed to. But, of course, we have a way to manage this problem. Remember, that methylation cap we added to our RNA at the beginning is mainly there to block RNA-chewing enzymes from destroying it. But now, RNA polymerase II's C-terminal domain is just way too phosphorylated for those negative elongation factors to come in and stop things again. So now snipped and missing a 5' cap, this junk RNA is just begging to be chopped up. And incredibly, there's an RNA-chomping enzyme ready to party in this exact circumstance. In human cells, this worker is called XRN2. This Lockheed Martin-ass name is fine, I guess, but the East scientists did way better here, naming the equivalent enzyme RAT1, which is sick because we're about to go rat mode to put a stop to transcription once and for all. RAT1 will grab onto this junk RNA coming out of RNA polymerase II and shoot along it like a missile. Once it reaches the end of that little RNA tail, it is actually the perfect shape to slam into the bottom of RNA polymerase II and physically knock it off of our DNA strand, terminating the transcription process. And this is called the torpedo model of transcription termination. It's over. We did it. Pole 2 is now free to go off and find new genes to transcribe, and our RNA transcript is free to get capped. If we go back to our freshly synthesized RNA, a new capping protein will join the party and add a whole bunch of adenine letters to the end here. Both ends of our RNA need to be capped to maintain stability. The main reason we have this poly-A tail at the end here, scientists figure, is to be kind of a freshness signal for this RNA. Even capped like this, RNA is still pretty unstable, but this long tail will degrade over time, getting shorter and shorter, so your cellular workers can assess the, freshness of any RNA that it comes into contact with and choose to destroy crusty old RNA that's past its use-by date. Maybe. But wow, let's just very quickly review the whole process and really lock it in. When it's time to make a new protein, your cellular regulators will loosen up the chromatin fibers containing our target gene. DNA has a bunch of signals that our transcription apparatus can bind to. We've got the promoter here at the start of the gene, and usually we have enhancers upstream that regulators will bind to. If the conditions are right, the TAT binding protein will bind to the TAT box, assembling all the TF2As, Ds, Bs, and Es needed to build a pre-initiation complex. The mediator will join the party and help stabilize the whole structure and help TF2H activate polymerase II. Pole 2 will then shoot out of the pre-initiation complex, instantly break down long enough for the new RNA to get a 5' methylation cap, and then get started back up with new modifications that will allow it to chew through all the histones that would otherwise block transcription. At the end, polymerase II is going to pass the 5' UTR and transcribe the polyadenylation signal, which will attract more workers that snip that fresh RNA off and drag it away to be processed. Now snipped and missing a 5' cap, this junk RNA is just begging to be chopped up by XRN2/RAT1. They join the complex and go rat mode, torpedoing into everything, pushing polymerase II off.
Okay, let's see.
Hi.
2, 3, 4, 5, 6, 7. So I have everything. Right? Okay, let's see. Now I currently 2 days left. 8,250. See?
Hi.
Just a bit over 9,000. So that's the trash situation. The horrible situation. And 50 enemies. And activity. Alright, let's go here. And do the thing.
I hear Orignium singing.
Off and fully terminating transcription. And we've done it, right? That's part 1 of the central dogma right there. Finished. We've gone from DNA to mRNA, right? But let's check out our freshly minted mRNA transcript as we gear up for final processing. Huh, that's weird. What are all these yellow bits in here? Welcome to the plot twist, folks. We've gone through so much already to get to this part of the journey. But remember, our goal for this video was simple. We're exploring the details of how your cells turn your DNA into mRNA. And that's what we've been synthesizing this whole time, right? Wrong. This strand right here, this is a eukaryotic special. As a lot of you probably know from school, bacteria actually follow this simple central dogma chart. DNA gets transcribed into mRNA, which then gets translated into proteins. Pure, simple, efficient, and it all happens in the same place at practically the same time. But that is not the game you play. You and every other eukaryote, from trees to baker's yeast, have a lot more work to do. Instead, what we've watched this whole time is RNA polymerase II synthesizing a special new class of chain, precursor mRNA. Of course, right? Pre-mRNA is just the raw information encoded in our DNA. For reasons we're about to explore, your genes are packed with air quotes useless little segments that don't code for protein. These are called introns, and we're going to color them yellow from now on. The orange segments actually do code for protein though. Those are called exons. All we have left to do is cut out these introns and stick our exons together so we have the right set of instructions for our ribosomes. So yeah, let's go back to this chart then. Plot twist, the real journey of this video is to use our DNA to synthesize precursor mRNA that will eventually get edited down into sleek, refined messenger RNA. To accomplish those edits, we will meet one of the most incredibly complex systems hidden in your cellular machinery. Your mRNA editor is this wild, roiling collective of workers called the spliceosome. How the spliceosome does its job is honestly hard to describe, but we'll cover the basics reasonably well in this video. But that's not good enough, because I figure you're like me when I first learned about this ludicrous complex in school. I figure you're practically screaming at the screen right now, asking, why do eukaryotes have to make things so complicated? And trust me, the why of the spliceosome will make this entire journey so incredibly worth it, because there's always a good reason for complexity. But let's not waste any time. Welcome to Plot Twist Part 4, discovering the secret superpower you have hiding in your spliceosome. I want to be clear here, because this video was already so long, we're only going to cover the very basics of precursor mRNA processing. We'll save a much deeper look into splicing and its machinery for a later video. You're going to see why in a second. Either way, the spliceosome has two main jobs. It needs to recognize and bind to both ends of this intron, and then it needs to figure out a way to cut the intron out at both ends while stitching our exon segments together. Now, we've seen moments where proteins can bind to specific DNA segments or mRNA bits, like the polyadenylation signal. But what's going to reliably attach to both ends of this intron? In answering this question, we get to meet one of the coolest classes of molecule. Check out our cast of characters for this one. To splice mRNA, we're going to need subunits U1 through U6. Let's go ahead and zoom in on U1 and see exactly what we're dealing with here. This first piece of our spliceosome reveals an incredible proof of how your cellular activity is managed. Does U1 look kind of like weird? It might, because U1 is actually made up of both RNA and protein. Specifically, this twisty strand is small nuclear RNA. Have you ever read that like 90% of your genome doesn't code for anything? Turns out a lot of the nothing coded in your DNA actually codes for little RNA machines called small nuclear RNAs. Remember from the beginning of the video, 1,000 years ago. Since RNA is single-stranded, it can twist and fold into lots of different shapes, just like the protein workers that supposedly power everything we do. Keep that fun little fact in mind as we move forward. So when you combine these wee little RNA twists with a protein assistant, like what we're looking at with U1 here, you get one of the most powerful and best named biological agents in the world. U1 is a deep breath, small nuclear ribonucleoprotein. And I know I said this was the best named thing in the universe. That right there is way too much of a mouthful. So folks in the business call little guys like this a snurp. He's a snurp. I don't care what you say. This fact alone is worth the price of admission. I love the words in this discipline. How could you not? And say that out loud. Snurp. Snurp. It is physically impossible to talk about snurps without a little smile on your face. They're so great, and they do such nifty work. But let's get down to business. The protein scaffolding in U1 is organized around this core piece of RNA. Check this out. This coil of RNA letters is directly complementary to the code at this end of our intron, the 5' splice site, which means U1 can bind to our pre-mRNA at the exact right space at the exact right time. This is the incredible power of RNA. We can use RNA workers like U1 to simultaneously bind to chemistry and information. But let's just see this in action first. Let's edit our precursor mRNA and get out of here. Step 1, we gotta assemble the spliceosome complex itself. It starts off simple. U1 actually binds to the 5' splice site during elongation and then goes on to help assemble the full spliceosome as elongation is playing out. Splicing mRNA actually happens at the same time RNA is being transcribed. And you know what? One day I'll have enough GPUs to render transcription and splicing happening at the exact same time, but if I tried that now, I would probably burn my house down. Speaking of which, if any of y'all know somebody at NVIDIA who could hook me up, I would really appreciate it. I got big ideas, and boy howdy am I ever ready to sell out. Either way, for now, let's just be cool with animating these processes separately. After U1 binds, the U2 SNRP is going to get recruited to the other side of this intron. U2 will bind to the branch point of this intron. Then we're going to meet the next 3 SNRPs all at once. U4, U5, and U6 here are better known as the tri-SNRP, because you know there's 3 of them. The tri-SNRP and U2 are going to do the actual splicing business, once the tri-SNRP gets into position right about here. So the first big thing that happens is U1 will hand off the 5' splice site to the tri-SNRP. U4, U5, and U6 will work with U2 to do the actual business of splicing. U1's job is done now and will mosey off to find another intron further down the transcript. We're now ready to get down to the real business of splicing. This full spliceosome will use ATP to reshuffle some pieces to fully incorporate the 5' side of this intron. That'll eject some pieces of the U6 SNRP and pretty much all of the U4 SNRP, which will help wrap this intron around the catalytic business end of the spliceosome. All this is going to set the stage for our big player, the NTC protein complex, which will bind to basically where U4 left and form the floor of our almost fully activated spliceosome. The active site is now fully ready to go. We just need to push the 2 ends of this intron together so they'll bind to each other instead of our exons. To do that, the spliceosome will reshuffle itself even more to get these 2 ends of the intron closer together. And finally, the spliceosome will snap into a much tighter conformation, finally putting our 5' splice site close enough to this branch point at the other end of the exon. This is the perfect configuration for the first real step of the splicing process, which is called branching. Basically, our 5' splice site will stick itself to the branch point on the other side of our intron, which means that down here, 1/2 of our exon has been completely freed from the intron, but up top we still have another intron bond to them. So we're going to shove these guys even closer together, and this is going to be tight enough that both halves of our exon are going to want to be together way more than they want to be with that intron bond. So they'll snap together while this looping intron, called the intron lariat, just kind of gets snapped off. Our exon is ready to go while our intron is ready to recycle. And changing the view real quick too, let me pull this part of the spliceosome open to show you our freshly spliced mRNA transcript. Nice. We're going to send that off for final processing, while the rest of the splicing machinery disassembles itself ahead of the next reaction. And I mean, it was cool, I guess, to see that in its full molecular detail, but for my money, that was a little bit hard to follow. One day I'm going to make a massive video explaining all of these different colored subunits and all of the very cool and very deep organic chemistry that's happening here. But let's dial the complexity down a little just to illustrate an introduction to what's going on. And we'll just show the business end of the splicing reaction. No U1 handoff, just U2 and the tri-SNRP, cutting an intron out. So let's take it from the top. Again, U1 is going to bind to our 5' splice site, while U2 grabs the other side of our intron. U1 is going to bring its side of our intron to the tri-SNRP, and then, bail. The tri-SNRP and U2 are then going to churn through a whole bunch of ATP so they can rearrange themselves enough to push the 2 ends of this intron together, bringing us to the actual splicing reaction, which has, again, 2 steps. Step 1 is called branching, where our 5' end gets shoved onto the branch point of the other side of this intron. Step 2 is exon ligation, where we'll squeeze this whole thing together even harder so our 2 exon pieces get glued together. The exon will then leave, and the intron lariat will be left behind to get chopped up and ready for another round.
Okay. So another 2 pulls. Another 1-ish. Oh. we're still rising from here. So 200 here. And 320 there. So one pull from those tutorials. Let's teleport there.
сценарий жизни. И поэтому все на это и обратили внимание.
Нам идут донаты. ЖГ, живи, Максиму респект. Написал нам аноним с сердечком, отправил нам 1000 рублей.
Another day of beautiful sounds. Do what you must, Professor. I'll do everything I can to help.
Yep.
Clearing the way for the rescue.
Do it your way. I'll keep you covered.
Feeling better?
Insignificant insects. On the other side. Watch my shots.
Feeling better? Sorry. I couldn't weather this storm.
Oof. I thought it was done for.
Feeling better?
Hey, yo. Hey, yo. Hey, yo. Not bad. Not bad at all. Mhm. 155. Nice, nice. Nice, nice, nice. Another crate. 20 of those. Oof. Okay. So I can pull 30 now. Right now. And I have 20 extra.
I've always wondered where the line is, you know, of saying like tortilla versus just tortilla, and especially as opposed to tortilla. It feels racist.
Tortilla is fascinating because that's a
AI is going to cure all disease.
I am convinced that someday I will be able to ask an AI to cure cancer.
It's something that you hear a lot as the justification for why we need to be building as powerful an AI as possible, as quickly as possible. And I can see why it's so tempting. In fact, I spent a year of my life trying to get into the field of AI for medicine because I found it so promising. But recently, a paper that I've read made me start to question whether we really are on track to build AI that's going to, for example, cure cancer. Perhaps we're not as limited by raw intelligence as I thought, and instead we're limited by something else. And by focusing on the wrong thing, we're kind of costing ourselves time. I almost did actually get a job in that field, and last minute I kind of decided that there were more qualified people with a biology background who would be able to do a better job. But I didn't stop believing in it, because I do really think that some of the things that AI has managed to achieve in medicine are already pretty incredible. So let me tell you about one of the success stories. There is an AI drug discovery company called In Silico Medicine, and they have a drug called rentosertib, which treats a, by all accounts, very horrible condition called idiopathic pulmonary fibrosis, a chronic scarring condition in your lungs, which is fatal usually within 5 years. And so having a new drug for this condition would be literally life-saving for people. This drug is not yet through stage 2 of clinical trials, so I'm not claiming that it's going to work for sure. But getting a drug even to this stage is actually really impressive. And that's because of how traditional drug discovery works. Basically, it's a giant funnel, a very time-consuming and expensive funnel. Here's how that goes. The first step in this pipeline is called preclinical research. And the very first thing you want to do is pick a disease and then try and figure out what proteins are involved in either causing it or worsening that condition. So here's one thing I didn't really understand until I started looking into all this stuff, but proteins are pretty much implicated in everything in the body. They do most of the functions in the body. So if you can find a target protein that's implicated in the disease, that is a big first step, because that will be the target that your drug is trying to fix. Okay, so how do we find a target? Well, this is really hard. Traditionally, this comes from years of academic research, where researchers will compare, let's say, healthy tissue with unhealthy tissue to try and figure out which genes are implicated, which genes are transcribing, etc., etc. So it is a very, very tedious process to try and find a target. This stage often takes 1 to 3 years on its own because it takes such a long time to show that there really is a causal link between a particular protein and a disease. Now, this is the first stage that In Silico did something quite different. They used a massive amount of data, including omics data, so stuff like genomics, and also papers and grant applications and things. And their AI platform was able to ingest this massive amount of data and propose a particular protein as a target. Now, the thing is that this data was already available to human researchers and researchers using current tools, but it's such a massive amount of data that it is sort of hard to see the signal in that whole sea. But that is something that AI can do fairly well. And so they proposed that TNIK is a protein that is implicated in this disease. Okay, so you found a target protein, but the next step is that you want to find a molecule that can do something to this protein. The way that this is traditionally done involves a lot of brute force. So this company might have a library of thousands, if not millions, of chemical compounds that it will test against this protein. Apparently, this is usually done by robot arms. I think that's very cool, but as you can imagine, it still takes a really long time to do because of just how many molecules you're trying to test. But eventually you will get a bunch of hits. So these are molecules that seem to do something to your protein. But a hit is not a drug. You see, the hit might be toxic, or it might not dissolve in water, or it might be destroyed by the liver. And so what the chemists at the company then need to do is they need to tweak that molecule until eventually they improve all of these properties and make it more drug-like. Most of the hits are just not going to work out. But over the course of, let's say, another couple of years, the chemists will find some molecules that could potentially be a drug. Then those molecules are put through mandatory safety testing, which involves 1 to 2 years of testing on animals like rats and monkeys and dogs, as well as a bunch of other safety tests. So all up, before you've tested on a single human, you've already spent like 5 to 8 years developing these drugs and testing thousands, if not millions, of molecules. And that is very expensive. So let's see how In Silico did it differently. So instead of going directly to the point where you're testing a whole bunch of molecules in the lab to see if they hit your target protein, the idea with AI medicine is to try and design molecules that are more likely to hit that target protein on a computer first. There have been massive breakthroughs on these AI molecular design tools. The biggest is probably AlphaFold, which you might have heard of. But they aren't perfect, so it's not like you can perfectly predict which molecule is going to react with your target protein. You still do need to test it in the lab afterwards. But the point is, instead of testing thousands of chemicals, you could be testing far fewer. And so the whole process could take a lot less time. According to In Silico, this whole process only took about 18 months. They tested only 80 molecules. So the cost of this preclinical research was about 1/10 of what it would have been traditionally. And the benefits don't stop there. The next stage is called phase 1, and this is where you're not trying to figure out if the drug works, but you're just trying to figure out if it's safe in humans. So you give the drug to humans who are perfectly healthy and see what effect it has on them, if any. It's very early days for AI in medicine, so only about 24 drugs designed by AI have even gotten to phase 1. But of that 2024, there is some slight evidence that they are slightly more likely to make it through phase 1 than non-AI drugs. The caveat is, of course, this is a very small sample, but it does seem like maybe AI is better at predicting the safety of molecules, which helps them go through phase 1 slightly more often. But this is where AI seems to hit a wall. You see, all of this stuff is, of course, time-consuming and costly, but it's nothing compared to the clinical phase, especially the phase 2 and phase 3 trials. It costs a lot to run these, and most drugs will end up failing. In fact, 90% of drugs will fail in the clinical trial phase. When you account for the cost of all of the failures along the way, every drug that comes to the market on average costs between $1.5 billion and $2.5 billion each. The preclinical part, the part where AI definitely seems to be making a difference, only accounts for about 1/3 of the total time and a bit less than 1/3 of the total cost. So it's really the clinical part that is the real bottleneck in drug discovery. And yet, so far, we haven't had much evidence that the AI tools really help with that. This drug from In Silico Medicine is currently halfway through phase 2 trials, but we have good reason to think that AI might not really help accelerate this part of the pipeline. To understand why, let's think about an analogy. Imagine a genius locked in a room with internet access. This genius is supposed to be like a general superintelligence, like imagine ChatGPT, but like much, much better. Now, how useful is that actually going to be in medicine? Well, for some types of science, it seems like it would actually be very useful. Like in my own field of quantum mechanics, if you gave it the rules of quantum mechanics, it would probably be able to derive a lot of different theorems about quantum mechanics, like, for example, how quantum computers work. It might be able to discover new quantum algorithms, and that all seems very useful. But in medicine, there's a very different constraint. So yes, textbooks about biology are on the internet and therefore are part of the training data of this genius. But does that really help? I think one example that really opened my eyes is mitosis. Mitosis is the process of cell division, which you might have learned about in high school biology. And given it's in a high school biology textbook, I figured it must be very simple and we must understand it completely. Wrong. There are hundreds, if not thousands, of proteins involved in that process where we don't really have any clue what they're doing. And so if the genius was trying to figure out something about mitosis, they wouldn't be able to do it from their locked room because there's so many unknown unknowns. Like, we just don't even know what the proteins involved really are. And so how would they be able to figure out what they do? To do that, you would actually need to do experiments, and from those experiments, gather data. So in some lucky circumstances, human beings have done those experiments. One great example is the data behind AlphaFold. The AlphaFold AI algorithm is trying to solve a fairly simple problem in biology. You take an amino acid sequence, and you know that this string is going to form a protein, but when you put it in water, how is that protein going to bend? Like, will it fold up in a crazy shape like this? Predicting this shape is so important because of how vital proteins are, and their function is often related to, for example, where they have pockets that molecules can bind to. So knowing the shape a protein is going to fold into is super useful. The problem seems simple, but it wasn't easy to solve. In fact, for 50 years, humans collected data about specific proteins, and they would figure out what their protein structure looked like with painstaking experiments. In fact, one of my friends did his PhD in biophysics, and he said that there were people in his department who had spent their entire PhD just trying to find out the structure of a single protein. Now, all of that data gathered using blood, sweat, and tears was put into what's called the Protein Data Bank. This is an incredible resource, and it's only because it existed that people at DeepMind were able to take that data and figure out how an amino acid will fold up into a protein fairly accurately. This breakthrough was called AlphaFold, and honestly, I think the algorithm is very, very beautiful. I was super impressed by it, so I made a bunch of videos about how it works. So I don't want to minimize at all the achievement that these AI researchers made. But I think we have to also realize that it wouldn't have been possible without that data. The problem is that this kind of high quality data becomes rarer and rarer as you go from simple things like single proteins to more complex interactions, to cells, to tissues, to organs, all the way up to the whole body. Because at every one of those stages, the complexity, the number of molecules, the number of unknowns just goes up insanely. And so even with a general intelligence, we wouldn't be able to really do anything to kind of predict what happens on the bigger scales without the data. And that's what's going wrong with these clinical trials. The biggest part of clinical trials is trying to figure out, does this drug work in the body? That means that we can't expect an AI model to just be able to simulate what happens in the entire body based on just what we know about the molecular level. The molecular level is just way more simple than the full human body. To figure out what's happening on these bigger scales, we would need to do a lot of experiments, probably over a much longer time, to really be able to understand them, and then to make the data that would be used for AI models to then be able to simulate them. But as it stands, we have a lot more data about the simple stuff than the more complicated stuff, which is why AI really helps at the top of the drug discovery funnel, where it's more about trying to figure out how molecules will interact, versus the bottom, which is more about the safety and efficacy across the whole human body. This is one of the points made in a great paper called How AI Can and Can't Cure Cancer. And it's a point that I think maybe I didn't understand, and perhaps other more tech enthusiast people might not understand, because they haven't really grappled with the complexity of biology before. So I really appreciated having this pointed out. I should disclose something quickly though. So this paper was written by a researcher at the Future of Life Institute, and the Future of Life Institute is now supporting my videos. But all of these opinions are my own from reading the paper myself. Like, the Future of Life Institute didn't look over this script or anything like that. But I still thought I should just mention it. Anyway, if you do want to check out that paper, there is a very flashy website for it. One thing I learned from reading it is that the quality of data in medicine is actually pretty bad. So the best sort of long-term health data that we have often comes from health records, but those health records aren't really designed to, help figure out what's happening to the patient over time. They're really mostly there for billing data. And so that's just not that useful. And the extent of data that we have on most patients is just from standard blood tests, which barely scratch the surface of all of the crazy stuff happening in the human body. Not only that, the paper pointed out that there is actually quite a replication crisis in medicine itself. So you might have heard of the replication crisis in other fields, where a researcher will see a result from one of their colleagues and then go to try and replicate it, and they just don't get the same result. Now, the reason why this has become so common is because there's a lot of pressure in research to publish positive results. So if you were to test out some sort of drug or intervention and you found no result whatsoever, you generally wouldn't be able to publish that, which hugely skews the kind of results that do actually get published. But having high quality data is absolutely critical if we want AI to help us with medicine. I mean, remember that in silico medicine was only able to speed up the target discovery by mining high quality omics data that already existed. But if this data is so critical, then why isn't there more of it? I think the problem might come down slightly to the incentives in science, where there isn't that much reward for just collecting a huge amount of data and making it available for everyone. That's why the Protein Data Bank was such an amazing project. It's also kind of rare. But there are some projects like this that have been doing an incredible job. One of them is the UK's Biobank. This is an incredible not-for-profit project which started in around 2008 and collected data from more than 500,000 people and is going to follow those same people for up to 30 years. These volunteers have given all kinds of data to this study, including, samples like blood samples, doing all kinds of state-of-the-art medical tests, and also answering questions about their life and lifestyle. So much emphasis in this AI for medicine stuff is focused on making general intelligences like ChatGPT better, but I honestly don't really think that that's the best use of our resources. You see, a single data center might cost in the billions, but a single research study like the UK Biobank would only cost in the hundreds of millions. And that data is so much more valuable when it comes to AI for medicine. You see, with AI drug discovery, you might say, oh, well, we'll just wait until we have, super intelligence, and then that will solve everything. That will just be able to simulate the whole human body. But it can't, because we don't even know a lot of the basic facts about how the body works. To be able to do that, you need to get data. Well, then you might say, oh, well, that's fine because the superintelligence will, come up with all these robots to do all of these experiments. But the thing is, experiments on biological organisms are rate limited by biology. You have to wait a certain amount of time for things to happen in a body or in a cell, and you can't rush those things. And so if we don't start to prioritize that sort of study, not only are we misallocating resources, we're losing time that we're not going to get back. Hey, before you go, can I tell you about a charity that means a lot to me? It's called FarmKind, and their mission is to end the cruelty that's involved in factory farming. Take, for example, the life of the average egg-laying hen. She'll live in a tiny, cramped cage, smaller.
Brutally efficient, as always.
Have you consumed enough today? Consume. Have you told a friend?
Your dad, your sister, your brother's computer, and Intel Honey.
Please fill out this quick survey for 15%. Our product is a total consume. Follow us on Facebook, like us on Facebook, urge you to hashtag.
Didn't you see it? It was in the box. They've always got food with them. We eat to live. These guys live to eat.
When I was a kid, I remember watching commercials on TV. What's funny is that I think I remember them more than the actual cartoons I was watching. Their vibrant colors, catchy tunes in my ears. Sometimes they literally made me say,
It's lots and lots of jets and planes.
What started off with a want quickly festered into a need, a sickness of consumption, wanting more and more. From the time I could process words, I knew this is what I needed. I grew up in a world full of click here's and save there's. But now I sit here in the greed and consumerist hellscape I've created for myself, and I wonder what if? What if I had more of a sign? Did I miss something along the way? Did I...
No. Come on.
How does one react when faced with a daunting, alien-like, impossible-to-comprehend entity? Some might say panic, some might say ignore it, but the film Over the Hedge says something different. Conform. Give the entity a name, explore its secrets, profit from its existence. The thing is that we as a species struggle to push back against that in which we don't understand.
Place because on this show we like to say things.
Oh, would you please just stop being so fucking pleasant?
Yeah, he's embracing the future there, and you're just holding us back.
Oh, I hold you back, all right. From extinction.
It's the same reason why when you start thinking about your existence for too long, your brain often resorts to just finding ways to distract the feeling of human ignorance. As social beings, we want to fit in. We want to not just survive, but thrive. This is a snippet from a movie from a time period in which branding was on the verge of something new, something horrifying. As a kid, I had no idea what the message of this movie was, really. I knew it was funny. I would say I'm a crazy rabbit squirrel all the time. Oh, and the THX scene would scare the living shit out of me. But this scene, the hedge named Steve, was much more than just a plot point. It wasn't just a catalyst nor an opportunity to animate a weirdly liminal scene, and it honestly wasn't even that much of a joke. It was a metaphor I should have understood sooner. Oh, shoot, where are my manners? You haven't seen Over the Hedge? Let me break it down for you. Over the Hedge is a film that follows a raccoon protagonist, RJ, who has been doing a terrible job of finding food. With his back up against the wall, he decides to try and steal from a bear cave, the mother lode of colorful, whimsical, ultra-processed food. He takes only what he needs, but falls victim to the whimsy and just decides,
just take what you need. Just take what you need.
Ah, fuck it, I'll take it all. On the verge of escaping, he's caught in the act with a red wagon filled with the brim of all of the bear's food. He tries to talk his way out of it, buys himself a little time, but doesn't consider...
So, technically, not stolen. Oh no! That was close.
Now, RJ faces an ultimatum. Find and replace all the food for the bear, including the red wagon, the blue cooler, and of course Spuddies, or die. What this sets in motion is a riveting heist film where RJ must manipulate creatures of the forest to find and replace everything he stole, navigating a suburban utopia/dystopia of opportunity but also danger. It's fun, hilarious, and over-the-top dramatic. And it's way too real. The Great Pacific Garbage Patch doesn't look like this. Somewhere in between California and Hawaii lurks a monstrosity that is over 3 times the size of France and is so large that calculating its mass is almost impossible. The rough estimate is 100,000 tons, 1.8 trillion plastic pieces. And yet we can't actually really see it.
Let's do it for some bad luck.
In other words, you right now, me right now, everyone on really see it. In other words, you right now, me right now, everyone on this planet right now has each contributed at least 250 pieces of debris to this monster.
In short, news sites and blogs use fake photos because the real thing just isn't that exciting to look at.
It lies there, floating across waves like a giant fungal growth on the skin of the earth. It morphs in shape, its microplastics dissolving under the sun. It moves unpredictably and poisons everything around it. The cleanup efforts started a while ago, but I barely made a dent. What I find so fascinating about the garbage patch is that I can't actually comprehend its size. My brain just won't allow me. 100,000 tons is heavier than 740 Boeing 777s. What's worse is that the number is playing it on the safe side. Advanced models changed our initial understanding of the patch, which gave us these numbers back in 2018, by the way. It's been 8 years since those numbers were published, all of which has the asterisk that this mass was growing exponentially. This isn't even involving the trash that is sunk below the surface, which, by the way, makes up 70% of all marine debris. Although my math is crude and likely off in some capacity, that means the trash visible to cameras and humans is less than half of what's actually lurking and under the patch. At least we gave it a name, though. Something so unfathomably large, stretching the bounds of our science and feudal minds, at least got a cool name. Personally, I'm just gonna call it Steve. Here's the thing. This essay so far has been easy to write because it's just assumed we all suck. We're all terrible people who have ruined our planet and created a monster so massive it is expanded beyond our scientific capabilities of measuring it. But it isn't that simple. When we are born, we aren't just tasked with overconsumption as our main goal. We want to survive, but we don't need to do much more than that. Instead, we are conditioned. From the time we can see colors and exponentially increasing as we understand language and symbols, we are conditioned to consume. Think about it, advertisements, TV shows, social media, everything around us is telling us consume. And over the hedge, Vern is the leader of the animals in the forest, stuck in the days of old hunting and gathering, and is a bark connoisseur.
Okay, this is great.
And I hated him when I first watched this movie. He's too old-fashioned, tries to deliberately stop the plot of the movie on multiple occasions, you know, returning the food and all that, and I had to see his ass one too many times. He's only about surviving the winter. That's so lame. It isn't until RJ comes along that Vern is actually forced into living a little, though it does take a long time to convince him. Slowly but surely, the animals begin to explore what lies beyond the Steve, where they find heaps and heaps of food, colors, and fun. Whimsy.
Get it? I understand. This is something that you're just not open to.
First they consume with hesitancy, then they consume with ease. The characters themselves really flesh out into personalities along the entire opportunistic spectrum, from severe caution to legitimate manipulation. Just like any good film, they all go through a certain amount of character development as well, with Vern likely going through the most. He starts off with his old-timer hunting and gathering mindset and finishes the movie basically completely embracing this consumerist lifestyle. All of this comes to a boiling point in the climax of the film. The final 20 minutes or so demonstrate an absurd level of stakes where, after over-consuming, the animals find themselves in danger after being captured.
I believe someone phoned about an animal problem. Male. Do you in fact have an associate's degree from Vermtech? Reptile. Except Texas.
RJ somehow avoids being captured and has all the food he could ever want and finally can give it back to the bear from which he stole, right where this video essay started. But instead, he has a change of heart, rescues his friends, and sets off a nuclear bomb on the exterminator and the Karen that they stole food from. Hell yeah. But here's the thing, nobody ever stops consuming at the end of this film, really. The lesson, in the end, is to conform to the consumerist suburbia without over-consuming to the point of being shamed.
Kind of anticlimactic. Shoot!
Interesting. It has been 20 years since Over the Hedge released in theaters. Since then, it has been rewatched, re-released on streaming services, and memed almost into an entirely different plane of existence. But something you may find surprising, especially if you were like me and grew up in an era of physical newspapers dying, is that Over the Hedge is based off of a comic strip of the same name, released in 1995. Cartoonists Michael Fry and T. Lewis are still publishing the strip today, and you can see all of them in their beautiful glory online. The comic strip itself has a very similar vibe actually to Calvin and Hobbes, which is ironic considering how some believe this comic's popularity stemmed from Calvin and Hobbes ending in 1995. Anyway, RJ compared to his much more Bruce Willis-y film counterpart is not so lovable in the comics. He constantly lies, portrays himself as an intellectual, and can't be bothered really with anybody other than himself. He has no character development like the film, which kind of makes sense, it's a comic strip. You'll see him hyper-obsessed with human society, holding soft drinks, brain rotting on his phone, and staring longingly out at the suburban lifestyle beyond the hedge. Meanwhile, Vern is cautious yet more easygoing in the comics. He's intelligent, caring, and serves as a wonderful counter-protagonist to RJ. I think what I love the most about the comic strip is that it can provide commentary on super recent events. It's quite strange seeing RJ and Vern discuss social media or Bad Bunny. It makes me wonder how the movie would have tackled that hot topic. At the same time though, I kinda live for that early 2000s nostalgia. Don't worry, we'll talk about Endfield soon, we're getting there. But what I would like to shed a light on besides all that I just described is one key difference between the Hollywood plot of Over the Hedge and the laid-back Sunday easy read feel of the comic strip. In the comics, RJ and Vern are really in the same boat from the beginning. They are creatures of the forest, live together, and strictly stay on their side of the hedge. Sure, RJ is obsessed with human culture, but he doesn't venture into what lies beyond, really. In the film, RJ doesn't only convince everyone to venture into the dangerous, lucrative suburbia beyond Steve, but he also is an outsider. He's completely different motives from these animals, and up until the very end, he's content with letting them die to save himself. But fortunately, the film takes a much more wholesome approach at him saving his friends and blowing up a neighborhood instead. But let's be honest here, the biggest difference between the comic strip and the movie is one word. Conformity.
The hedge has been constructed.
Welcome to 19862 Mellon Circle in Ashburn, Virginia. Your home is actually sited on the picturesque 10th green. As a gated community, Belmont Country Club is known for its spectacular Arnold Palmer signature 18-hole golf course.
This is Ashburn, Virginia. For the most part, it's just like any other average suburbia in the United States. Identical houses as far as the eye can see, shopping malls for the average consumer, and of course some beautiful golf courses.
This is Data Center Alley in Northern Virginia. 40% of the internet passes through.
The reason why I stopped you is we're not allowed to take photos.
If you look at a data center map of the United States, you might see something odd. They're clearly all over the place, some in hotspots around major cities, yeah, that makes sense. And then there's a massive collection of them in Northern Virginia, right in the middle of the suburbs. Why? Typically, I mean, I know data centers are a problem, but they're far away from me, right? Well, it's time for some internet history. In the early 1960s, MIT professors Leo Beranek, Richard Bolt, and Robert Newman are contracted to launch ARPANET, basically the internet before the internet. They successfully linked MIT research labs with Harvard, Stanford, and UCLA, which was really freaking cool for the time. Plus, it was near Washington, D.C., so it had added protections and benefits. Not to mention, it was a government-funded project.
There was this organization in the government called ARPA that was interested in computer networking. The Advanced Research Projects Agency is directed to moving technology in areas that are important to national security.
Fast forward a few years, the internet starts to actually take off and become developed, and in 1990, ARPANET would be transitioned over into a commercial entity. What that means is now one of the first ever internet exchange points in existence, think of it like a hub for all things internet data related, is located in Tysons Corner, Virginia. Like right next to Ashburn. Fast forward some more years, and Northern Virginia finds itself with one of the most expansive networks of fiber optic access in the world. Why? Because the existence of the internet itself has roots here. But one must not forget what we're talking about in the first place. Consume, consume,
Consume.
Half of all of the new demand for electricity in the U.S. in the next 5 years is expected to be driven by data centers.
And consume more than 4% of all electricity in the U.S.
The way it is right now, all of the customers are paying for those infrastructure upgrades.
Last year I read this essay by an author named Ronald Wright called A Short History of Progress.
Seeing a lot of petitions like this one, nopowerlines.org.
And it talks about essentially how civilizations and empires collapse.
This was the sound at Laura Evans' home in suburban Chicago last spring.
He presented an overview of various empires throughout history.
Generators kicked in at the data center 1,000 feet from her backyard.
And he basically identified that when these empires collapsed, they pretty much exhibited the same trend of behavior before the collapse.
People losing their mind, rightly so.
You say, this is the future. What do you say to that? Build it somewhere else.
And the whole idea comes down to resources and how we use them.
Listen, burn, right? This isn't something you need to be afraid of.
As an empire grows, it needs more and more resources to sustain itself. This would require continuously expanding the territory of your nation.
By then, the platforms are so big that it's hard for users and for businesses to leave, and so they are willing to put up with quite a bit of abuse.
It has completely changed our economy from a failing economy to one of the strongest local economies anywhere in the country, and the data centers have done that.
And this just keeps happening until eventually you reach a singularity of sorts. There's this tipping point where the excess and the resource consumption becomes too much, and all of a sudden, the empire starts to fall apart.
Jealous of him? Yeah. He's embracing the future, Darren. You're just holding us back.
Once they realize that we're about to slip over the point of no return, time and time again, they refuse to pump the brakes.
Sometimes we need to just be able to say things.
And the civilization just lives in denial of its own collapse until it ceases to exist, until all the resources have been exhausted. And what I found rather disturbing while reading this is that this is how it feels to live in America right now.
But if there's one thing that I pray that all of you hear from what I have just said, is that all of us,
Ben Folds was recruited as the musical director for the film Over the Hedge, and he contributed 5 songs to the collection. The soundtrack arrived in stores on Tuesday, but the movie opens nationally this weekend.
Well, what we just accomplished was setting the tone for the picture. The picture has its unique tone, and it's an interesting thing to watch a movie. I've never done this before, to watch a movie with no music at all. And you know, to the extent that the music takes you to you know, another side of the story or another side of the visual, or brings out something about a character that is yet to happen.
You don't stop. How great I am.
The soundtrack of Over the Hedge is, for lack of a better description, sadistically real. It's sad, energetic, witty, and satirical in all the right ways. Written and performed by Ben Folds, the lyrics of these songs perfectly exemplify how living in suburbia is to live by standard of privilege and blissful ignorance. Case in point, rockin' the suburbs. Let me tell y'all what it's like watching Idol on a Friday night in a house built safe and sound on Indian burial ground. We're rocking the suburbs, feed the dog and mow the lawn, watching mommy balance the checks while daddy juggles credit cards. These lyrics are so on the nose, I have no idea how DreamWorks actually approved them. In fact, this set of lyrics is different from the original, which are somehow even more on the nose. Other songs showcase different emotions, and what's even better is the themes of the movie match the lyrics Ben Folds uses. For example, Family and Me discusses how everything will be fine eventually and don't worry about it. How Great I Am, got myself, yeah, I'm the man. Looks grim right now, but pretty soon we'll be laughing about it. It plays during the title sequence before RJ has found friends. Heist plays, well, you guessed it. The animals start stealing from the humans and they're dumbfounded by all the fascinating inventions they use. Follow me into the great unknown, where pink flamingos crow, diet soda flows, and what you take magically regenerates. On supermarket shelves, the ovens clean themselves. It plays during a time where the animals haven't fallen victim to their own hyper-consumerist hubris yet. They're still just blind to its utopian image. And my favorite above all, the song Still, the backing track you're listening to right now, discusses how giving the impression that everything is fine is actually a logical fallacy. You want something that's constant, and I only want it to be me. But watch even the stars above. Things that seem still are still changing. This is just a brief snippet of a soundtrack that encompasses all things absurd, from the animals stealing from the humans to the existence of suburbia in of itself. What's even better is that unlike most animated movies that just randomly throw in some popular artist top hits, Ben Folds' music not only tells a story through lyrics, but through specific instrumentation and expression as well. I can't go into more detail here due to copyright, but let me know in the comments if you like a full breakdown and I'd be happy to rant over on my second channel where I don't really care about it getting copyright hit. Regardless, Ben Folds did a masterful job creating a soundtrack that is self-aware while also capturing something more, something deeply human about how our existence isn't necessarily the best one, but we don't know how to fix it. And for a kids movie,
What do you think it is about Over the Hedge that has made it so popular with readers and editors for so long? It's a two-level concept. It's got your classic us versus them structure, and Hedge's case pitting the animals against the encroaching human world. That has a nice contemporary vibe. And yet, like all anthropomorphic concepts dating back Aesop's fables, our animals are largely just people in critter costumes. So there's an interesting tension. The animals, ostensibly on a moral high ground as victims of the suburban sprawl, are also seduced by the good life. Dumpsters, broadband, Twinkies, the cast of byproducts of a human-adjacent existence. We can all understand that ethical tug-of-war.
This video and its creation is not made to convince you to stop consuming. We are all victims of a machine that keeps on taking, and there's no easy way to disconnect. The treadmill production will continue to exponentially increase in speed until we've dried up every natural resource on Earth. No, this video is not the solution to conformity. Instead, it is simple in hopes of raising awareness for the treadmill itself, the tear between our personal values and what our ignorant culture wants us to believe, the hedge between us. The film Over the Hedge is about whimsical creatures of the forest having to conform to the dystopian, lucrative suburban landscape that lies just beyond their comfort zone. Their forest is surrounded with infrastructure, their way of life is not only about survival but about exploitation, and they must now become human or die of starvation. By the end of the film, they too consume like we do. The need for more is temporarily fulfilled and the garbage patch continues to conquer the Great Blue Marble. Take those themes, throw in a banger soundtrack, and you have a film that has persisted with a cult following over 20 years after its initial release. So much so that I'm now talking about it on YouTube. However, this is a tale of irony. Our suburbia, our problematic, exploitative suburbia, is being surrounded by new, high-tech infrastructure. It's being bulldozed, gated, and forced to either adapt or die. Consume more or die trying. The hedge has been constructed, all will conform. Your ways of being have not evolved. This new world
and all of its consumers to be a Walmart and Over the Hedge, May 19th. Never stop consuming. Don't even think, just do. Don't complain, don't analyze, just ignore and comply. Consume.
Lift your head. We are over the hedge now. And every beast will eventually resent its cage.
At the end of the day, Zenless is a mixed-gender gacha game and nobody forced them to do that. The people in charge decided to include men in order to draw in male enjoyer players. As such, it is their responsibility to treat male and female characters equally. For a long time now, there's been an ongoing narrative that Zenless Zone Zero hates men. Is that true? Kinda? Yes and no, it's complicated. All I can say for sure is that the way Zenless Zone Zero treats men is bizarre. From a design, story, voice acting, hell, even fan service perspective, they have equal, if not better, treatment than the female characters. But from a gameplay standpoint, they continuously get screwed over. Also, here's a kick-ass question: where are the men? Post-launch, almost 2 years later, Zenless has only released an additional 7 male characters compared to the 27 female characters, almost 4 times more women than men. Before talking about the actual treatment, I want to make something perfectly clear. I have no problems with a gacha game being a waifu game. If the developers want to only release female characters, then by all means do that. I would still play Zenless even if it only released women.
Say the line, Barb!
I've been playing gacha games since 2012. I've played waifu games in the past and I will do it again if they catch my interest. But as someone who enjoys both female and male characters, I despise when a gacha pretends to cater to male enjoyers. I especially hate it when it comes to Zenless because it genuinely has some of the best men I've seen in a gacha game. Granted, that's a very low bar. If you started playing Zenless post-launch, you may not know this, but during its marketing campaign leading up to the official release, Zenless heavily featured the male cast. Specifically, they pushed Billy and Lycon. Billy, Nicole, and Ambi were the first characters ever revealed, the trio becoming the faces of the game. This combined with Billy being a fun, quirky Dante wannabe with insanely energetic, fluid, gorgeous animations, he instantly became a fan favorite. Lycon was officially revealed during the first beta. He and Miyabi were the most popular male and female characters, and ever since, Lycon alongside Miyabi have become a sort of secondary mascot for the game. Did you know that they used him in 2 official collabs? The first was for an Ashton Martin car paint job. Also, Rena was there. The second was for a Coca-Cola collab alongside Ellen. Bro, why are these not official skins? They look so good! Better than that stupid schoolgirl outfit, that's for damn sure. Now, Zenless only launched with 4 male characters and 11 female characters. Clearly, the developers had a bias towards female characters at the start, and that's fine. But given the quality, success, and popularity of those 4 men, the developers should have changed their future plans and prioritized making a more even split amongst the male and female cast going forward. It doesn't need to be a perfect 50-50 split, but something like, let's say, 60% female releases and 40% male releases would have been fine. Now let's talk about those delicious 4 men. In version 1, Billy truly got to shine by constantly bouncing off of the Cunning Hare's hilarious Three Stooges routine. Also by having the ever-present mystery of where he originates from and how powerful he truly is. Throughout the game's lifespan, we've gotten multiple small hints that beyond all the goofy exterior, Billy is harboring some insane secrets. Anton and Ben were great supporting cast during the Bellabog chapter, which primarily focuses on Colita. Their unique personalities got to shine, and they both helped in crucial ways throughout the chapter. And of course, Lycon stole the show during chapter 3, the suave gentleman that would stop at nothing to help Phaeton in their mission to find and save Rain. And with a surprise reveal at the end of the chapter that someone hired him to watch over Phaeton in secret. Not only was the writing for these characters great, their designs were drop dead gorgeous as well. The cool, wacky, goofy robot, the large, cuddly bear, the manly construction worker, and the gentle, calm, and collected wolf. A surprisingly wide range of archetypes considering the low number of men available. Due to the phenomenal designs, amazing writing, and heavy push in the early marketing, Zenless drew in a large amount of male enjoyer players. And these players were vocal. The popularity of Billy and Lycon was no secret. The constant showcasing and great quality of its male characters at launch gave the impression that Zenless would somewhat evenly release and treat male and female characters. But as we all know, that did not happen. With all of this in mind, how Zenless has treated its male characters is truly baffling. Before I go through the history of these characters, I want to explain something. When I talk about the gameplay of these characters, I am doing it under the assumption of the average player. What does that mean? It means free to play or low spending. Your average player does not have a fully built Cinema 6 character. They were not blessed by RNGesus himself and given perfect god equipment, they do not have a maxed out premium weapon, and they certainly do not have a maxed out team of limited time premium units. Your average player has any given character at Cinema 0. If they really like the character and are really lucky, they might have Cinema 1 or Cinema 2 if they're extremely lucky. Their equipment has okay, decent stats, and if they have a premium weapon, it's only one copy, but more likely than not, they are just using a good free-to-play alternative. As for teams, honestly, it depends on the character and the player. If a character requires a team of premium limited time characters, your average player most likely will not have those characters when they release, but they might be able to get them on a rerun. And even if they do get them on a rerun, most likely they're just going to be Cinema 0 and they're not going to have a premium weapon, because at the end of the day, gacha games are gambling simulators and most people are going to be very unlucky. There's also something to be said about the average skill level of the average player. The majority of players are logging in after getting off from work or getting home from school or whatever to have some fun and blow off steam. They are not learning perfect skill rotations and executing crazy combos, which does impact the average player's ability to max clear, aka 3-star content. The first post-launch male character was Seth in version 1.1, an A-rank character that was borderline useless. Sure, you could use him as a universal support, but he never offered anything that literally any other support didn't already offer, and dramatically better. His only real use was in a Jane team, but even then there were better options for Jane. His gameplay sucked, but luckily he was great in the story. Although Jane was the main focus, he got a lot of screen time as well. We learned some of his backstory and saw him try his best to help out innocent civilians. And all of his interactions with Jane were adorable. Surprisingly, he and Jane became a really popular ship within the community, still going strong to this day. As for his design, personally, I am completely neutral about it. I don't hate it, don't love it, but a lot of people love him in all of his twink glory. And this right here, problematic gameplay and great everything else, is the male character pattern of Zenless. Later released in the second half of version 1.3, and he is a really interesting case. We officially met him in the version 1.2 story, where he was an important secondary cast member. We learned a bit about him, and we had a one-on-one showdown against a giant orangutan. His 1.3 release also gave us his story quest, where we learned more about him. And I mean, come on, look at him. Clearly, obviously, this is an amazing design. The only thing that would make it better is if he took off the jacket and was shirtless. Like, bro, this dude looks dope as hell in this picture. Imagine if this was his actual design. I'm just saying, he should take off the shirt. All in all, he has a phenomenal design and good story, but his gameplay is where things get weird. At release, he didn't have a lot of use. Although he's a good stunner, he was tailor-made for ice and fire teams due to his enemy elemental resistance reduction. The problem is that in version 1.3, Soldier 11 was the only fire DPS available, and she just wasn't good. Lighter was a nice upgrade for her, but it wasn't enough of an upgrade to really justify summoning for him. However, there was Ellen, who was an ice DPS, but Ellen already had a good team with Lycon as her stunner, and yes, you could run a double stun team with Lighter and Lycon, but the ice reduction wasn't enough of an upgrade to really justify doing that with Ellen. It was better to just use a more traditional support with Ellen and Lycon. He was great on paper, but in practice he had no true purpose. He had decent stunning capabilities, but why use him when you could use Lycon, Colita, or Ambi, characters that you most likely already had and already invested into. It was smarter to just use your existing stunners and save the summons you would have spent on Lighter for somebody else. However, with the release of Miyabi in version 1.4, he finally had an ice main DPS that he could support. Well, sort of. While yes, Miyabi did benefit from his ice reduction, due to her being an anomaly unit, she didn't benefit from his stunning capabilities all that much. Realistically, you weren't going to use Miyabi with Lighter. Instead, you were going to use Miyabi with Yanagi or make a mono ice team and use Miyabi, Lycon, and Sokaku. It wasn't until the release of the fire attacker Evelyn in version 1.5 that Lighter finally, truly had a purpose. Then the ice attacker Hugo released in version 1.7 and Lighter was no longer trapped to one team. He had some variety. Sadly, throughout season 2, he has suffered due to the fact that we got another fire stunner, Jufu Fu, and she was a tailor-made support for the shiny new Rupture class and new Miasma shield mechanic. Of course, you can still use Lighter in any team where you theoretically would have used Jufu Fu. By no means is he bad in those teams. Like I said, he's a decent stunner, but his main value comes from pairing him alongside fire and ice characters due to the resistance reduction. And early on in version 2, we only had Yi Xuan as a Rupture unit, and she is Ether. It wasn't until version 2.3 where we finally got an ice Rupture unit that Lighter could theoretically support, and then we got Banyue in 2.4, who's fire Rupture that once again Lighter could theoretically support. However, because these characters are Rupture, it just makes more sense to use Jufu Fu since she is tailor-made for Rupture units. The entirety of Season 2 has prioritized the Rupture class and Miasmic Shield mechanic. Again, he's not useless by any means, but he has suffered. Harumasa was released in version 1.4 as a free electric attacker unit. Everybody got a free copy of him simply by logging into the game, but only him. You still had to summon for his weapon. The main story did not heavily feature him since it was focused on Miyabi and concluded the Bringer arc. He honestly wasn't even an important secondary member. He was just kinda there in the background, but he did get his own dedicated character quest, and it was one of the better character quests in my opinion. Great exploration of his backstory, a tragic story of sickness, betrayal, death, and finding the strength to carry on and live your life knowing that any day your sickness could end it. His design is pretty good. Doesn't speak to me personally, but he certainly has his fans. The gameplay of Harumasa at the time of release was a very underwhelming damage unit. While not bad necessarily, he certainly got the job done. He required so much more investment than any other premium main damage unit in the game, even more so than characters like Ellen and Zhu Yuan, who were released 4 versions before. Not only did he need duplicates in his premium weapon, he needed the best supports the game had to offer if he hoped to compete with the likes of Jane Doe, Yanagi, and especially Miyabi, who were the peak of power at the time. Harumasa at his strongest was equivalent to a mid-level Yanagi, if that even, and I specify her since they are both electric units. Again, you could max clear content with him, but your average player would and did struggle to do so. Astra's release in 1.5 was a great upgrade for him, helping him somewhat comfortably max clear content if, once again, you invested into him. However, throughout version 2 and the great Rupture / new character Giga Shelling, Harumasa has greatly struggled. In version 2.6, he got a buff which has certainly helped, but because of the rampant power creep and shilling of version 2, even with those buffs, Harumasa is nothing special. Currently, he is an okay DPS once again if you invested heavily into him and his current premium team. But the greatest tragedy of Harumasa is the fact that over a year after his debut, he has yet to receive his first rerun That's right, if you did not get him in version 1.4, it has been literally impossible to get him. Players have been begging the developers to give him a rerun, but for some reason, they refuse to do so. My only guess is that this has to do with the fact that he was given away for free. Because he was given away for free, they have this like weird thing going on with him where they just are going to make us wait a really long time to finally get a rerun. That makes literally no fucking sense, but it's the only reason I can come up with is the fact that he was free, so that caused some weirdness with his rerun. They'd rather give us our 5th Ellen rerun instead. Yuzuha, a character that was released in version 2.1, recently got her first rerun in version 2.6. The current update as of me writing this. What the fuck? Seriously, bro, what is this nonsense? Version 2.6 would have been the perfect time to give Haramasa his first rerun, coinciding alongside his buff. The fact that that didn't happen is truly absurd. Honestly, at this point, I genuinely have no fucking idea when Haramasa could possibly get his first rerun. At this point, it just doesn't make sense anymore. I truly do not understand what is happening. Next up is Hugo, which is a very complex case. Hugo himself is the full package. Great design, amazing story, and decently powerful. He was the main focus of the 2-part Mockingbird epilogue of version 1. A really well told story taking a massive deep dive into his tragic backstory and his upbringing alongside Lycon, as well as their philosophical separation. In the present, we got his reunion with Lycon, his heartwarming family relationship with Vivian, and his insane plan to bring down those who wronged him. Hugo is one of the best written characters in Zenless, and it's not even close. In terms of gameplay, he released in the second half of version 1.7. He was the final version 1 character to release. While not the strongest character from a raw damage standpoint, he was a really good ice attacker main damage dealer, having a unique gimmick where his skill and ultimate would do increased damage based on the enemy's stun gauge percentage and instantly delete the gauge during the stun window. Sadly, he almost instantly fell off of a cliff, and there's 2 reasons for this. The first is lack of dedicated support for his unique gimmick. Most damage dealers in the game have supports that help boost their specific gimmicks. For example, Silver Soldier Ambi, who released in version 1.6, the update before Hugo, got 2 dedicated supports for her gimmick. Aftershock damage, the A rank stunner Pultra and the S rank stunner Trigger. Eventually, she got some extra support in season 2 with her direct buff and Orphe being a sub DPS belonging to the same faction as her. Hugo got no such upgrades. Not only has he not gotten any direct help, whether it be a dedicated stunner, support, sub DPS, or a direct buff. And for some reason, the character that should have been his direct support, Vivian, has literally 0 synergy with him. For some reason, she's an anomaly sub DPS, and while she's really good in that role, she has no place in a Hugo team because of that. Which is bizarre because not only do they have the story connection, they belong to the same 2-person faction, Mockingbird. Usually, characters that belong to the same faction have some sort of synergy with at least one other member of the same faction. Currently, as of me recording this, the only other faction that only has 2 characters is the Stars of Lyra, which has Astra and Evelyn. The difference is that those 2 characters actually have perfect synergy with each other. Astra is an amazing support for Evelyn. So currently, as of me recording this, the only faction to not have some characters that have good synergy with each other is Mockingbird, Hugo, and Vivian. Every faction Bang Boo requires 2 members of the same faction to be in a team to activate their B skill. The only exception to this is Robin, the Mockingbird Bang Boo that only requires 1 member to be in a team to activate their B skill. So once again, truly, these 2 characters have 0 synergy with each other, and it's just weird. The second reason Hugo fell off of a cliff has nothing to do with him and everything to do with Miyabi. She was the undisputed most powerful character in Season 1, a true monster. Because of this, she unintentionally ruined the ice element. In order to try and force people to summon for the various new shiny main damage dealers of Season 2, most of the Season 2 bosses have massive ice resistance. Hugo is an ice character, so he heavily suffered from this decision. Want to hear something really funny? Ellen got a direct buff in version 2.0. However, this was the same version that introduced Mevarok to the game, a boss with massive ice resistance. In the exact same version that was supposed to save Ellen, Miyabi accidentally made her buff worthless. The sad truth is that there is nothing inherently wrong with Hugo's gameplay. He's actually a very unique, fun character to use, but because he belongs to the same element as Miyabi and he has yet to receive any direct support for his niche, he kinda sucks. So as I was editing this video, I remembered something about Hugo. Originally, in his first beta version, he had access to aftershock damage. However, in future versions of the beta, and eventually when he fully officially released, they removed that completely from his kit. He no longer had access to aftershock. This is important because that means he no longer had access to Shadow Harmony, an equipment set specifically tailored for aftershock damage. This dramatically lowered his full power potential because almost a full year later, Hugo still does not have a dedicated, tailor-made equipment set for his specific gimmick, totalization. But here's the thing, this is not unique to Hugo. In fact, every single post-launch S-rank male character does not have access to a tailor-made equipment set made specifically for them. Not a single one, which is absolutely insane. Why is this the case? I genuinely have no idea. But I know what you're wondering. What about the female characters? Technically, it is true that not every single female character has access to a tailor-made equipment set. The difference is that eventually they will. And I can comfortably say this because of Zhao. Zhao, when she launched in version 2.5, did not have a tailor-made equipment set for her. But she will soon. I believe in version 2.8, there's going to be an equipment set specifically tailor-made for her. I'm going to make a very big claim here and say that if Hugo was actually a woman, none of this would have happened. Pan Yin-Hu released in version 2.0 as a defense rupture support. He actually had great value because he was the only rupture support in the game. His ultimate can also give a small heal, which is a great bonus. Yi Xuan, the extremely powerful Void Hunter rupture damage dealer that was released in version 2.0, needed him to access her full potential. A free copy of him was given away for free through an event in 2.0, which is nice. Of course, he was eventually replaced. Lucia became the dedicated S-rank premium rupture support in version 2.3, which isn't a problem, to be clear. Honestly, the fact that he lasted as long as he did is impressive, and he still functions as an easy to acquire, free-to-play friendly alternative if a player either doesn't want to summon Lucia or if her banner isn't available. Panda suffers from a story standpoint, kinda. Now, to be clear, not every single character in Zenless needs to be this super complex character that we go on a multi-hour epic to explore their character. It's fine for some characters to simply exist in the background to chime in every now and then, but Panda doesn't really do that. Even though he is always there at the temple throughout the entirety of Season 2's story, he rarely makes an appearance, and when he does appear, he doesn't really say or do anything. Mostly just gives basic words of encouragement or talks about food because he's a chef and he really likes food. Now, again, he doesn't need to be super story relevant, but what makes his lack of utilization so weird is that he is one of the masters of the temple, often training the other members. So theoretically, we should be seeing him more often since Bell and Weiss are also being trained at the temple and spend a lot of time there. I'm fine with him not being super relevant to the story. Once again, not every character needs to be, but I wish we would interact with him more often. More than anything, he suffers from being an A rank, since he isn't a premium S rank character that the developers are trying to cram down your throat so you'll spend more money to get him. He simply faded into the background. Then again, there are plenty of other A rank characters that did make a lot of appearances and we interacted with very often in the story. Seth played a major role in Jane Doe's special episode. Lucy was one of the main characters of the Outer Rim story arc, so Kaku is usually around and we usually talk to her whenever Section 6 gets involved in the story. Ben and Anton played major roles in the chapter 2, I believe it was, the Bellabog chapter. So yeah, honestly, like I said, Panda is just kind of disappointing. I wish we interacted with him more often. Monato. Oh boy, where do I even begin? Monato is a very complex situation, so I'll try my best to be brief. He is one of the best written characters in Zenless, and it's not even close. Whoa, major deja vu. He played an important role through Season 2, constantly joining Phaeton in their various adventures. His strength helped keep everybody safe, and he was able to use his various connections and knowledge to help Phaeton, Spook Shack, and even the Temple. Also, he's hot. Please, Monato, crush me with your massive muscles. Oh my god, sorry. but for some insane asinine reason, he's an A rank. He was released in version 2.3 as an A rank fire rupture damage dealer, and to this day, this is one of the most moronic things MiHoYo as a company has ever done. A character that has been frequently featured and important to the story and very popular amongst the community, being released as an A rank alongside a completely random, never before seen character of the same class, and yet she's the S rank? So fucking stupid. Here's an easy fix. Make Monato an S rank and Yidhori an A rank. Boom, clean, easy, quick, done. Literally the only reason he's an A rank is because he's a man. If Monato was a woman, she would have 100,000% been released as an insanely overpowered S rank character. From a gameplay standpoint, he's surprisingly strong considering he's an A rank. However, he's nowhere near strong enough to actually be worth using. Due to him having A ranked stats, he's never going to be able to compete with S rank damage dealers. He also requires Cinema 6, amazing equipment, and premium supports in order to make any sort of splash. Worst of all, his gameplay is very clunky. I'll give you one quick example. He has a counter attack that deals a good chunk of damage. In fact, it's one of his main sources of damage. However, you cannot cancel into the animation. You have to stop whatever attack you are currently doing, wait for a second, and then activate the counter skill. This makes one of his main sources of damage very unreliable to use. Due to his low stats and clunky gameplay, there will never be a situation where Monato is a better choice than Yishuan, Yidhori, or any other future Rupture character. The only reason you would play him is out of a personal desire to do so, which is fine in and of itself, but Monato deserved better treatment. The final stab against Monato is the fact that in the very next update, Zenless released the S rank Fire Rupture male damage dealer Banyue. Bro, what the fuck? Genuinely, what the actual fuck? This goes beyond stupidity. This is straight up madness. Monato is the perfect example to show that Zenless has a bizarre antagonism against its male characters. And to be clear, I know I haven't gone in and explained what I mean by that, but I want to go through and talk about the history of the male characters first before I explain what I mean when I say Zenless has a weird relationship with its male characters. Don't worry, we're almost done. There's just 1.5 characters we need to talk about. Speaking of Banyue, he is the most confusing case. Him releasing directly after Monato in version 2.4 as another Fire Rupture unit is bizarre. Genuinely, it is super weird. Eventually, having elements and classes overlap is fine, but at release, there were still two other elements that he could have been, physical or electric, and personally, I would have made him physical. Similar to Monato, he also had some controversy surrounding his release. When the version 2.4 beta first came out, he was an extremely powerful main damage dealer, and then he immediately got nerfed into oblivion. Suddenly, he was slightly weaker than Yid Hori, who in turn was already a very middle-of-the-road damage dealer. The main reason this is a problem is due to Banyue's mechanical complexity. He is the most skilled expressive character in the game, having multiple button inputs, adjust timing, cancels, and combos. Now, compared to traditional action combat games like Devil May Cry, Bayonetta, and many others, he is still very simple, but within Zenless, he has the highest skill ceiling. Due to this ceiling, a player that is devoted enough to learn his complexity should be rewarded with an equally high payoff, but instead of being one of the strongest characters in the game, he is weaker than Yid Hori, who funnily enough is one of the simplest characters in the game. Can somebody please explain to me why the head empty octopus lady is stronger than the master martial artist robot tiger? More than anything, it's simply bad game design to not properly reward your player for learning the most skill expressive character you have to offer. As for his story, he was well treated. Version 2.4 took a deep dive into his backstory. He constantly interacted with various characters, which let him establish and explore his characterization. The ending section had a great emotional payoff with him wanting to atone for his past mistakes. All in all, the only thing wrong with Banyue is the fact that he is disappointingly weak. Zenless version updates usually last 6 weeks, and character premium banners usually last 3 weeks.
Okay, let's pause and read the stuff because I can't otherwise. Defense resist or chain attack. Crit damage. Okay, what are the agent crit damage increased? Attack of agents with attack specialty is increased by 10%. That's fine. Attribute anomaly. Ultimate damage. Like that? Really? Why snap? Okay, let's find those stone. Okay, so just not attributes. There is no resistance. Ah, yes. You know what? I know who I want to use. I want to use this one. Except...
Let's fire it up! Where are we going? There's no class today.
Wanna...
Got a new ghost story to share?
Which alias should I use this time?
Great. More crit rate. Alright. It's fine. I think I need more attack percent. Yeah. Unfortunate. Yeah, attack percent. Let's look at. Retreat, please. Not sure. Not sure what I wanted. Twice into attack percent. Okay, that's attack percent. Normal proficiency. Attack percent, please. No. Crit damage. Okay, well, that's an interesting thing. For someone. Maybe. Give more attack percent, please. Nope. All right. Yay.
Where are we going?
3000.
There's no class today.
Let's see.
First 3 weeks we get one character, the next 3 weeks we get the second character, with the rare exception of Miyabi and Shunwang, which were both available for the entire 6 weeks of the update. Banyue is the only character whose banner lasted for 12 days. Not even the entire 2 weeks, 14 days. No, 12. The reason for this is that version 2.4 was shortened by a week because version 3.1, the summer update, lasted 1 week longer. In order to realign the schedule, they decided to remove 1 week from version 2.4. The reason this is stupid is because if you really wanted to realign the schedule, okay, fine, do that. But why screw over Banyue's banner specifically? You know what they should have done? Have Dialint and Banyue's banner be available from the beginning of the update up until the end. Just have them both simultaneously be available for the entire 5 weeks. Bada bing, bada boom, done. Everybody's happy. Nobody gets screwed over. I'm gonna quickly talk about 2 NPCs and you'll understand why by the time I'm done. Damien is not a playable character, but he was prominently featured in the Season 2 story teaser. This made it seem that if not playable, he would at the very least be important in the story. Sadly, that's not the case. He made short appearances in version 2.0, 2.1, and 2.2. And that's about it. Similar to what I said during the Panda section, it's fine to have a character that...
It won't hurt. I'll make it quick.
Don't get sloppy.
Hey! A flurry of thrusts. Keep it up.
He plays a small supporting role, but I find it odd that he was prominently featured in the story teaser trailer, when in the end, he doesn't do much of anything.
Yeah. Yeah. Missed the valid area.
It would have made more sense if he was replaced by someone like Izelda in the trailer, somebody who actually was important to the Season 3 story. Also, for some reason, he's wearing a Hollow Investigator outfit, even though he doesn't wear one in the game, nor does he have any connection to them. Damien is simply a corporate suit trying his best to climb up the ladder. I have no proof of this is pure speculation, but I think Damien was originally going to play a much larger role in Season 2. But something happened somewhere along the development pipeline and he was rewritten to have the smaller supporting role he ended up with. Yi Shi Yuan is in a similar boat. He was introduced in version 2.0 in a minor role, however in versions 2.4 and 2.5 he became a major focal point, undergoing massive character development and playing a key part in the story. We even got a boss fight against him and yet he's not playable. Genuinely insane. That being said, it was set up at the end of version 2.5 that he is going on some sort of self-discovery journey. More specifically, he's investigating Void Hunter weapons. Most likely he will return to the story at some point, whether it be in version 3, version 4, or version 5. Who knows, but I do think he's going to come back at some point, and when that happens, perhaps he will be playable. But truth be told, I'm not holding my breath. Zenless has an incredibly odd pattern of releasing male characters either directly before or alongside Void Hunter level characters. Currently we only have 3, Miyabi, Shunguang, and Yi Xuan. Void Hunters are the most powerful characters in the game and will give your account a massive boost in power. Combine that with the fact that male characters consistently get screwed over in the gameplay department, and it seems that the game is going out of its way to create weak sales for the men. Any character releasing directly before the Void Hunter or alongside them will suffer in sales if they are not a direct support for them, male or female. What's really interesting about this pattern is that almost every female character that has released directly before or alongside a Void Hunter has worked really well with one of them. Yanagi is an amazing sub DPS for Miyabi. Jufufu is an amazing stunner for Yi Xuan. Dailin is an amazing stunner for Shen Guang. Zhao is an amazing support for Shen Guang. Vivian is actually really interesting. She's not a good partner for Yi Xuan, but she is a good partner for Miyabi. 5 out of the 7 post-launch men have released directly before or alongside a Void Hunter, and only one of them has worked well with a Void Hunter. Panda, he's a good free-to-play support for Yi Xuan. This is not an accident. It's a pattern. I don't know why they keep doing this, but it's starting to get absurd. To me, it seems that the people in charge are forcibly trying to create this narrative that men don't sell in order to justify not making them. There is an interview with the developers released during the lead up to version 2. In this interview, they mentioned that they are aware of the love for the male cast. As such, they plan on releasing more male characters in the future. So far, this has been a complete lie. Now, the final update of Season 2, version 2.8, has not been released, nor has the drip marketing as of me writing this video. There are a lot of in-game hints that Billy could possibly get an S-rank variant in that update. If that happens, that means Season 1 and 2 would have the exact same amount of male characters. If Billy doesn't get his variant, that means Season 2 had less men. Either way, that interview was a goddamn lie. You could give them the benefit of the doubt and say that they will
Strength and finesse. Like a shadow. Reality and illusion. An opportunity.
Referring to Season 3 onward, but given the track record of MiHoYo as a company, I will not give them that benefit. But hey, they are more than welcome to prove me wrong. Oh my god, bro, when will this guy stop talking? What was the point of me explaining the history of male characters? Well, it's to show that the narrative that Zenless hates men is not true. But it's also not a lie. Like I said at the beginning of the video, the way Zenless treats its male characters is bizarre. On average, the men have great designs, good stories, equal fan service to the women. Usually, they only really suffer from a gameplay standpoint, and even then, it's complicated, like I've already explained. But here's the thing. The men aren't the only ones that suffer from these various complications. So do the women. Like I mentioned before, Hugo and Ellen both suffered from the anti-Miyagi killing throughout Season 2. Yet Hori and Banure are both disappointingly underpowered rupture main damage dealers, most likely in order to try and push people to summon Yi Xuan. Bernice was hardly present during the Outer Rim story arc, and even when she did appear, she was mostly just a joke character in the background, only being focused and developed in her specific character quest. Similar to how Harumasa was hardly featured in Chapter 1.5, only being showcased in his character quest. Silver Soldier Andy's gameplay at release was shockingly underwhelming, to the point that a large portion of the playbase were furious. Even post-buff, she still struggles to stand out, only being an okay damage dealer. It's even worse for Bernice. She also got a buff, and paradoxically, it somehow made her worse. I don't even know how that's possible, but here we are. Both cases being similar to how Harumasa post-buff is still underwhelming. Truth be told, there are a couple of women that are treated equally as bad, if not worse, than the men. So why is there a narrative that Zenless hates men specifically? Why does no one talk about the women? Well, it has to do with the amount of men that have released post-launch compared to the amount of women that have released post-launch. 7 men compared to 27 women. You heard me correctly. There have been almost 4 times the amount of women released post-launch than men. It's genuinely crazy. When a female character gets screwed over from a gameplay, design, or story perspective, it sucks, but it's not that big of a deal. There are so many women that some of them are bound to be overlooked one way or the other. For every Bernice, we have a Miyabi. For every Lucia, we have a Nicole. For every Silver Soldier Anby, we have the original Anby. And let's be honest, more often than not, the women are treated at the very least decently. It's rare for them to have something clearly, objectively wrong with them. Because there are so few men in Zenless, it stands out so much more when they are treated badly. Hugo has an amazing story, a great design, and at release, he was a good damage dealer. Not the best, but he got the job done. He's the full package. As long as you ignore the fact that the beta removed the aftershock damage that he originally had, leaving him in this really weird position where he's a good character, but he lacks a dedicated support or equipment. But besides that, he's the full package. To this day, being treated better than most of the female cast. The only thing wrong with him is the lack of dedicated supports for his unique gimmick and the anti-Miyagi shilling. But the shilling has nothing to do with him. Rather, it has to do with the atrocious anti-player shilling of the Rupture class and Miasma mechanic. The developers tried their damnedest to force people to summon Season 2 characters. Similarly, Lighter was the full package, his only fault being the lack of an ice or fire damage dealer to support. But eventually, we got Evelyn and Hugo. However, the remaining 5 characters of the 7 post-launch men all have obvious flaws. Seth, Minato, Banyue, and Harumasa all have glaring failures in their gameplay. Panda is oddly missing from most of the Season 2 story. It's a numbers game. The percentage of mistreated men is astronomically higher than the percentage of mistreated women. This makes it seem like Zenless hates men. But why are there so few men? Considering how popular Billy and Lycon were at launch, you'd think the developers would have made a more equal distribution of male and female character releases. Obviously, I don't know the actual reason, but I do have a theory. I believe that the actual developers, the people slaving away in front of a computer screen for hours upon hours, like male characters and want to make more. Hugo's and Lighter's full package, Banyue's incredible animations, Yishi Yuan verbally taking down the temple higher-ups, these things don't happen by accident. It's clear the real developers love the male cast. But the higher-ups, the people in charge calling the shots, hate men. It's no secret that Da Wei and the other heads of the company are gooners, or whatever the kids are saying these days. In case you didn't know, MiHoYo has a long, proud history of being pro-Rise, and let's be honest, some of these women are wearing the most obvious gooner nonsense I have ever seen. You're telling me this is a cop? She looks like a Party City stripper. I believe the higher-ups are essentially forcing the real developers to do all of this nonsense. And to be clear, I'm not talking about the fan service. I'm talking about mistreating the male characters. I've literally said it a billion times throughout the history of my YouTube career. I do not hate fan service, but there's a difference between good fan service, which I like, and bad fan service, which is made with the express purpose to steal money from sad, lonely, pathetic men. And sometimes women, but that's a little rare. Nerfing Banyue into the ground, not making Shiwa playable, prioritizing constantly shitting out waifu bait instead of having a more equal balance of male and female character releases. I know this sounds incredibly stupid. Why would the higher-ups purposefully sabotage their own games like this? Well, you'd be surprised what people will do when they think with their dicks instead of their brains. After all of the outrage and deserved criticism towards the mistreatment and lack of men, and the consistent failure of most of the Season 2 women, I really hope this is a wake-up call. Hopefully, Season 3 will have a more equal balance of men and women, and they will be treated fairly. If you want to have fan service, go ahead, have fan service. I like it. Amazing stories, amazing designs, amazing gameplay, amazing fan service. Like, give me equal treatment for the men and the women, and also just make everything high quality like it was in season 1. Seriously, the difference between season 1 and season 2 is so astronomically massive, it is insane. The most obvious example of that is the fan service. Season 1 had amazing fan service, but then season 2 did the most boring, generic, easy, like bottom of the rung fan service imaginable. It's so predictable and boring, bro. Give me gorgeous designs, gripping stories, engaging gameplay, the whole shebang. Oh, who am I kidding? We're gonna get 2 A-rank men. S-rank Billy will be released and be nerfed into oblivion. 15 more women will be released, and all of them will be dressed as Party City strippers with massive asses and titties bouncing all over the place. Waifu, 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 waifu! At the end of the day, Zenless is a mixed gender gacha game, and nobody forced them to do that. The people in charge decided to include men in order to draw in male enjoyer players. As such, it is their responsibility to treat male and female characters equally. Would you believe me if I told you this video was originally supposed to be 10 minutes long? It somehow ballooned out of control and turned into an almost 50-minute long video, bro. At some point, I need to learn how to stop talking. This is getting ridiculous. I want to clarify 2 things. I recorded and wrote the script for this video before version 2.7 release, which is why I don't talk about Billy. Also, I am uploading this video on March 26th of the year 2026, and I want to clarify that because as of me uploading this video, S-Rank Billy, or Silly as I like to call him, has not been confirmed to be releasing in version 2.8, and honestly, if you ask me, I don't think he's gonna release in version 2.8. I think he's gonna release at the earliest in version 3, and I think he's gonna be the Yi Xuan of version 3. He's going to be a part of a new element or class, and he's going to be this very powerful Void Hunter level character. I don't think he's going to be a Void Hunter. I think he's going to be Void Hunter level. Minuscule difference, but it is very important. Feel free to share your own thoughts about the whole male discourse of Zenless Zone Zero. I would love to read your thoughts. And of course, make sure to leave a like and subscribe if you enjoyed the video. Thank you so much for watching, and I will see you next time. Bye-bye.
What do you need me to do? I see Ash.
Oh my god.
In 1956, while test flying a new F-11 Tiger off the coast of New York, a pilot's windshield suddenly shattered and his engine failed completely. Investigators ruled out a bird strike. The real cause was far stranger. What happened? One more time, in 1956, while test flying a new F-11 Tiger off the coast of New York, a pilot's windshield suddenly shattered and his engine failed completely. Investigators ruled out a bird strike. The real cause was far stranger. What happened?
Big sneeze. Huge. Strong guy. Big
Yeah,
sneeze.
the plane had allergies. Yeah, so a bird strike is the aviation term for when a bird like flies into an engine or something like that.
Yes.
Like a Sully style.
It is not when the birds stop working to demand better.
Right, exactly, yeah.
Their method of seeking guild representation is threatening to blow up every plane. It's a pretty big threat.
So either it's that the thing that is causing it, the strangeness is from that being unusual, so you'd expect birds to be around, but if it was like, it was turtles that crashed into it, like that's kind of strange. It's like the thing was stranger that did a similar thing to bird strikes, or that it's strange that this should happen, like they just sort of forgot to glue in the windscreen on the test. Like there's some strange thing. I don't know whether there's like, I'm thinking there's different directions we could go with like what made it strange.
Yeah, something it being like it's not pressurized properly or something feels very normal, like plane stuff, mainstream. And so I'm like,
we've got to get more alternative with it.
Yeah, did the engine fall off and then hit the windshield?
Oh, how embarrassing.
No, Jarvis, but surprisingly a little closer than you might think.
Okay.
Did the windscreen fall off and hit the engine?
If you just start guessing parts of an aircraft, you won't quite get this. But you are you are closer than you might think.
Was the pilot accidentally flying from the outside of the plane? And so when you know, he's like, oh, Butterfingers, has to take the windscreen off to get the controls. And that's like, they don't even do that in Top Gun.
You wouldn't want to do that in an F-11 Tiger.
It's not going to be like ludicrously fast because of the era, but this is post like World War II innovation on like jet combat. I don't know that plane. Is it a...
We've broken the sound barrier at this point, right?
That is key. This is Grumman's first supersonic jet fighter, the F-11 Tiger. And so jet fighter.
Jet fighter.
So they did have to investigate. It wasn't something like it's riddled with bullets. So clearly there was like some kind of combat.
Fighter is interesting specification because where I was going to go, let me just get this out, maybe it's wrong, is like something about the like resonance or of going, like breaking the sound barrier, like a sonic boom or something could cause like the sonic boom, like it wasn't prepared for the shock waves, and then the shock waves caused it.
I think the speed is it's a fighter, and so it was meant to test its guns, and it was traveling faster than the bullet velocity.
Yes, it was.
So it fires out and just straight back into his face.
That's so funny.
Oh my god.
That's so funny.
It was a little more complicated than that, but I'm absolutely giving it to you. Yes, this was test pilot Lieutenant Thomas Attridge. He fired a 4-second burst from the 20mm cannons towards the ocean surface and then descended rapidly along his flight path at near supersonic speed. The cannon shells slowed down because of air resistance. The Tiger caught up. And when you said riddled with bullets, Jordan, yeah, right. It became known as the plane that shot itself down.
Oh no!
Attridge was fine, by the way. He crash landed, but he survived the accident with injuries. He returned to fly.
I don't think I'd want to survive. I'd be so humiliated.
The bullet struck the windshield, pierced the airframe, damaged the engine, caused total power failure.
There are not enough thumb screws in the world to get that story out of me. I would be like, I just bumped into like, did you know a new war started? It actually just started.
I think Aliens it was, actually.
Yeah. Look out, they're in the sea.
I think it was so crazy. Like the fish were coming with guns. Like I didn't even know. I was flying a normal non-fighter plane.
Don't worry, guys. I killed all of them. So don't look into it. They're all gone, and it's all set.
It tends to be quite difficult to lie to the Air Accident Investigation Branch. Where they tend to be quite good at figuring these things out.
Yeah, they're so good at plain stuff.
I really want anyone who is watching this to watch Tom's face as Jordan said the phrase riddled with bullets. It was one of the funniest. It was like, if you looked at dictionary definition of the opposite of a poker face, that was what Tom was doing in that moment, and it was very funny to watch.
The Lateral book is out now. Just click on the...
By
my hand, this endless conflict shall meet its end!
Well, I'm gonna wait for a bit.
Tiger. It's not going to be like ludicrously fast because of the era, but this is post like World War II innovation on like jet combat. I don't know that plane. Is it a?
We've broken the sound barrier at this point, right?
That is key. This is Grumman's first supersonic jet fighter, the F-11 Tiger, and
so
jet fighter.
Jet fighter.
So they did have to investigate. It wasn't something like it's riddled with bullets. So clearly there was like some kind of combat.
Fighter is interesting specification because where I was gonna go, let me just get this out. Maybe it's wrong. Is like something about the like resonance or of going like breaking the sound barrier, like a sonic boom or something, could cause like the sonic boom, like it wasn't prepared for the shock waves, and then the shock waves caused it.
I think the speed is it's a fighter, and so it was meant to test its guns, and it was traveling faster than the bullet velocity.
Yes, it was.
So it fires out and just straight back into his face.
That's so funny.
Oh my god.
That's so funny.
It was a little more complicated than that, but I'm absolutely giving it to you. Yes, this was Test Pilot Lieutenant Thomas Attridge. He fired a 4-second burst from the 20mm cannons towards the ocean surface, and then descended rapidly along his flight path at near supersonic speed. The cannon shells slowed down because of air resistance. The Tiger caught up. And when you said riddled with bullets, Jordan, yeah,
right.
It became known as the plane that shot itself down.
Oh no!
Attridge was fine, by the way. He crash landed, but he survived the accident with injuries. He returned to fly.
I don't think I'd want to survive. I'd be so humiliated.
The bullet struck the windshield, pierced the airframe, damaged the engine, caused total power failure.
There are not enough thumb screws in the world to get that story out of me. I would be like, I just bumped into like, did you know a new war started? It actually just started.
I think aliens it was actually.
Yeah. Look out, they're in the sea.
I think it was so crazy. Like the fish were coming with guns. Like I didn't even know. I was flying a normal non-fighter plane.
Don't worry, guys. I killed all of them. So don't look into it. They're all gone, and it's all set.
It tends to be quite difficult to lie to the Air Accident Investigation Branch. Where they tend to be quite good at figuring these things out.
Yeah, they're so good at plain stuff.
I really want anyone who is watching this to watch Tom's face as Jordan said the phrase riddled with bullets. It was one of the funniest. It was like, if you looked at dictionary definition of the opposite of a poker face, that was what Tom was doing in that moment, and it was very funny to watch.
The Lateral book is out now. Just click on the link to get your copy. Which children's song starts with the head of an ox, a house, and a camel, and ends with a sickle? I'll say that again. Which children's song starts with the head of an ox, a house, and a camel, and ends with a sickle?
S Club. We're gonna have a
Ain't no party like the head of an ox.
Wait, I'm remembering that. I always thought this was so strange.
Okay, well that's hieroglyphics, I'm assuming.
Ooh, sickle, Grim Reaper. Hiya.
What's the one that's pocket full of posies, ashes, ashes, they all fall down?
Ring a roses.
Yeah, ring a roses.
Ring around the
Oxy, house, camel, yeah.
Yeah. You know, it's actually a lot of people don't know this. That's a metaphor for having a house and a camel.
There's is Ollie Ollie Oxenfree in a song?
I found myself defaulting to nursery rhyme, but it may not be a nursery.
Could be Baby Shark.
It could be Baby Shark.
It could be Baby Shark.
Is it? Is Baby Shark the answer, Tom? Is it Baby Shark?
It's not. I'll to avoid any parents who are starting to have flashbacks. I'll just move us on from that and say no. Absolutely.
You should play it on the show a little bit.
Yeah.
That does start and end with Baby Shark.
I'm not head of an ox, house, and a camel.
What does the ox say? Side, sickle.
Wait. So let's think laterally about this, because I've just been thinking that. That's, by the way, that's like the phrase that we always have to say before we give an answer.
Yeah, it's like, and also with your spirit.
Yeah, and then we all put our hands in the air and we like Power Rangers into one.
Yeah,
lateral.
earth, air, wind, fire. I was thinking about it very linearly. And I was just thinking about lyrics to a song, but in what way could this be? Could we think outside of the box?
Yeah, I think it's fair to say that it doesn't start literally with these. They are ancient presentations of something.
I suppose if it's ancient, then the song isn't going to necessarily like rhyme or resonate in English now.
Oh, it does now.
Post-translation?
Oh, okay.
Okay. So it's still around, like, as an active thing that people sing.
Is the idea of like if you were to figure out what the modern day alternative to like the ox head, whatever camel is, that would be the lyrics. It's not necessarily that the song was like ancient and then has been translated. Yep. It's like like when people do badly described movie plots. You're like, yeah, technically, I guess that's what that movie is.
Yeah,
like Purple Josh Brolin makes Chris Hemsworth weak bad.
Yeah, exactly.
Yes, but I think, Rowan, you are far more right than you think there. Like, it's not just a bad translation.
Okay, so maybe it's what aside from not the literal translation, how about the lateral translation? Thinking laterally.
Whoa.
Wow.
Trademark symbol.
Wow.
Let's think laterally about this.
That's so powerful. Yeah.
What would you represent with an ox? Like, I'm guessing. I'm kind of just defaulting to how like unnecessarily macabre so many children's songs are. And
right,
going,
that's
like,
what I'm thinking about too.
But I guess sickle can also just be like, you know, harvest or trade or craft, you know.
Rowan, you said hieroglyphs earlier, and you're making a hand gesture now.
Yeah.
To try and figure out how would you draw the head of an ox? How would you represent the head of an ox?
Little. Do they have horns? Is that what oxes have?
Hey, it's your ox. You could just.
I would keep going with that hand gesture. That was pretty good.
It's like one of them. It's got little horns.
Yeah.
Anyone do this for a song? Anyone do a song like that?
For those not watching in video, it's difficult to describe that as other than looking like both the head of an ox and the thing we're looking for. Yeah, maybe connect those horns at the top. Maybe disconnect bits you've got at the bottom.
Is it?
Maybe just
ABC?
Yes, Jordan. You are absolutely right. Keep talking. So what children's song are we looking for?
Oh man, probably the ABC song.
Yeah, the alphabet song. Spot on.
The ABC song. I forgot the word for the alphabet.
Yes, the letter A, or Aleph, Alpha, that was based on the pictogram for an ox's head. And you accidentally demonstrated that so well, Rowan. B, Beth, Bet, Beta, that was a house. C, Gimel, that was a camel. And Zion was a weapon like a sickle or a short sword. Those were the very, very early pictograms that over so many years became the modern alphabet. So the kids' song is the alphabet song.
It kind of kept the A pretty solid. That wasn't too big. All the pieces are there, yeah.
That's pretty good.
I've done, on some podcast, I've ranted about the alphabet song and that I knew a different version of it when I was a kid, but I can't remember which podcast that was on. Have I told anyone here about that?
No. What possible other alphabet could there be, Thomas?
This was wherever I grew up. I think it must just have been the local teacher.
Allegedly that I grew up.
Well, the reason I mention is I don't know if this was local or regional hyper-specific, is that I learned A, B, C, D, E, F, G, H, I, J, K, L, M, and O, P, Q, R, S, T, U, V, W, X, Y, Z.
They've changed it. Dave changed it. Tom, they have changed it. There's like a new version of doing the alphabet that is that version. That they've now done because too many kids don't actually understand the LMNOP. Like that is too difficult for a lot of kids. So they have now changed. I don't know whether they've changed it back to your version of it. Or
No, I remember finding this. It's not that version either.
It's a different one.
The version I got taught, slant rhymes M and Z. And everything lines up better. Anyway, it's the alphabet song. The answer to the question is the alphabet song.
The version I learned was like ox head, scythe, and that was kind of it. Yeah.
Yeah, you were at Mesopotamia, right?
Yeah, that was us.
The Lateral book is out now. Just click on the link to get your copy. When it's safe to do so, Gerald will often reply =6 to his employees and co-workers. What is his job and why that reply? One more time. When it's safe to do so, Gerald will often reply =6 to his employees and co-workers. What is his job and why that reply?
It's really hard for my brain not to just go 6, 7 based on my kids' ability.
By the time this episode comes out, that'll be long gone, right?
I know, they'll be like, 6 what?
I found a thing while researching, and this is for a video that'll come out a long time from now. Things like that, weird expressions that are basically meaningless, have been going on for so long. I found an old reference, and I've got to explain a reference from like 1888 in a video to just a song title that became the equivalent of 6-7 for the 1880s.
That's beautiful.
It's so much context. It's so much context.
We've done some special bonus episodes reading a joke book from the 1700s, and a lot of those jokes you just get to the punchline, you're like, I got nothing. This is clearly something cultural that was really important at the time, but for me, I got nothing. Mm-hmm. Just like this question, why would you ever need to say =6? I've got nothing. This is nonsense.
Good segue.
Do you think we should focus more on the when it's safe to do so? Like what sort of boss is giving some safety instructions?
Yeah. When is it not safe to say =6?
Yeah, is it saying it that's not safe, or is it that there's other things going on and 6 is like the signal that it's safe? And why 6 and not 7?
When I say =6, everybody's going to run across the road. But if there's traffic, it's like, I got to wait. And then I'll say =6, and all my employees can run across the road. Why? =6 is the answer to something, right? That's like they've posed a question. Hey, boss, I got a real tough problem. 2 times 3. What's going on? And then when it's safe, =6.
Is there some sort of situation where people might be saying something that sounds like a simple maths problem? Like 24/4?
Yes.
Ooh, really?
Mm-hmm.
Oh, could it be like a sport? What was exactly his title? Did he get a title to? Who
We
did he
didn't
say
get a
this to?
title, no.
Okay, could it be like a? I wonder if it was one of those. You know how like when American football players are playing American football, the coach is always like, "We're going to run this play. We're going to run this," because everything's very mathematically laid out. And I wonder if it's like a
Sure.
code sort of thing of like we're going to do play 2 3 times. So I'm going to tell my team equals 6, and that way the other people don't know that that's what we're going to do. My team gets the code, and I only do it when it's safe to do so, because if we did it at a different place, we'd lose the game.
So code is a good keyword in there. Perhaps not in the way that you're describing it, though.
Damn.
This wouldn't work for a phone call or a radio message.
Intriguing.
Oh.
It wouldn't work for a phone.
So is there some kind of like thinking back to different types of code, like you've got Morse code and stuff like that? Is there one that's based around only 6 different sort of variables, maybe?
I'm now just moving my mouth, hoping that one of you will look at my face and think that it looks like
And go,
something.
yes, that's exactly
right.
Microphone's not working when you've come up with the perfect answer. What about like earthquakes? There's like category of different earthquakes, and that would involve a bit of like not being safe. But then the equals throws me off with that.
Equals is just an odd thing. Like 6 is a very clear message. Equals 6 is a weird guy. This guy's got something strange going on.
If it's not a phone call or radio message, what might it be?
I have pictured him just rolling a window down and shouting verbally to some people. Just like leaning out of his office.
I don't think that picture's right at all.
The text. First, come on.
Ah, okay. He writes it down. It's a visual message. It's not about the sound. He goes equals 6, and everyone looks and they go.
Is he doing it with his hands somehow? I can't even make that.
You've all missed a pretty obvious way of communication here.
Sign language, talking.
He texts it.
He texts it. Yeah, this is a text message.
That's writing it down. Okay, so
well, it is, but not by putting a pen unless you have a Palm Pilot from the 90s. Generally, you're not handwriting this.
I briefly thought about could it be some sort of text speak, and then I went, no, equals 6 is only going to be rude in text speak, whatever it is.
Equals 6 is it's like a colon P. It's a
little bit.
You know, it's like
a little bit.
I'm your crazy boss. Oh.
Not quite. I think, Danny, I'd drill down on that simple math problem.
Okay, what else can there be besides just
back to the numbers that make up 6?
3 plus 3. That's a pretty good one.
2 plus 4, 1 plus 5.
We're nailing it.
3 factorial. 3 with an
That's
exclamation
true.
mark. They text 3 exclamation mark. It's like equals 6.
Remember, this is a text message, and it's only when it's safe to do so.
What situations are there when people use texting in safe versus potentially unsafe moments? When is this important in someone's job?
And then I suppose the other thing we need to consider is if it's not safe to do so, does he not send them anything, or does he send them something else? Is also like a...
Doesn't send them anything.
When someone, what about when someone says 10-4? That would be like 10 minus 4, right?
Yes, it would, Danny.
Ooh.
Yes.
Okay. Now,
So
why
it's
do
just-
people say that?
10-4 is like message received.
It's
It's like I got it, man.
Yep, and when written down, it is 10-4, 10 minus 4. So what's his job, and why that reply?
Yeah, who does this? Because right now I feel like we've got a text conversation of people saying, yep, to each other.
Is it like military based in some way?
Who else might use that?
Medical, like hospital codes?
And has a job where it's unsafe to text while you're doing it?
Truck drivers?
Yes.
Oh.
So you've got the
What?
first part, truck driver.
he is a
Strength
truck
is one of those
driver,
things
and
where
he
you gotta
replies
use it or lose
equals
it.
6
So,
to
train
say
with me sometime?
10-4, but
10-4 means affirmative in 10 code. So yeah, that's truck drivers, law enforcement, others. It has its roots in CB radio, but if you are in that community, you might still text 10-4 just as instead of saying okay or anything like that. So why might you text back equals 6 to that?
Because it sounds fun.
Because it sounds fun. That's the whole thing. It's just him being.
Yeah.
It's just him adding a joke.
I didn't know that truck drivers would communicate with that sort of thing with each other.
It really wasn't that deep. It's just him being annoying.
It's just him being a cool guy.
Yeah, I really think that we were fine. I was totally fine with him having fun, but just going, why are truck drivers talking to each other?
The Lateral book is out now. Just click on the link to get your copy. When performing the end of Chopin's Prelude in D minor, Allegro Appassionato, some concert pianists depress 2 keys without making a sound. How does this help? I'll give you that one more time. When performing the end of Chopin's Prelude in D minor, Allegro Appassionato, some concert pianists depress 2 keys without making a sound. How does this help?
I'm going to sit out because I have I don't know the answer. I don't know the specific piece, but I feel like I have an idea that might come too close.
Is it something to do with resonance, so that certain keys actually resonate with other keys, and so if you don't press them and actually lower because the way the piano works is you've got strings inside the piano and it gets, it hits the string. So if you don't actually muffle the string a bit by pressing them, then they could resonate.
That is exactly what I was going to say.
So, I know nothing about music, so this is
pressing and holding down a piano key releases the felt damper off the strings, which means that they can ring. Which means you could put down, hold down notes that are a harmonic of the one that you're playing, or an octave or something like that, and it could ring sympathetically and make it louder.
Or literally, like, if you're really bored, you can just go to the piano and see how slowly you can press a key and not make a noise, and it's really fun. I mean, really fun.
That sounds fun.
I think you may be overthinking that a little, but you've got some key bits there. And the ending is fortissimo. The ending is very, very loud. You got that bit.
Okay.
But that's not quite the technique we're looking for.
Okay. So it's very, very loud and it doesn't make a sound. This sounds more like a Buddhist question.
I'm sure there are other keys being... Ooh, wait. There is a piece where the very ending of it is you slamming the lid of the keys down.
The piano lid?
Yeah, but you can't do that while you're holding a note down. But
you could do it if it needs to end in a scream.
I've seen Tom and Jerry. I've seen the Cat Concerto. You can absolutely do that. Your fingers just come out in a weird shape.
That's how you get the depression and the whatever, depressio. I don't know.
But if you hold down the keys to remove the dampers and you're percussively using the piano, then that would give something to resonate and be louder, but that's not very Chopin.
It would, but that's not why they're holding down the keys.
Is it because somebody else is plucking the piano from the inside and holding down the keys changes that sound a bit?
Yeah, a small mouse going along with... No.
I like this plan.
The prepared piano, that is known as, if you're putting extra things in your piano, such as mice and rulers and things to make your piano sound weird.
Prelude in D ends with a big old bang, we reckon. It's a really loud ending.
It is fortissimo. It is very, very loud.
Is he just screaming? It's like the pianist is screaming at the end? Just, ah!
No, it's regular musical notation here. There's nothing... No, it does not have a note that says pianist screams or anything like that.
Too bad.
And only some concert pianists do this. It's possible to play without doing it.
Do you need an extra finger to do it? Is it a bit of showing off?
Do you use your foot? Do you actually use your foot at the end? Like, are you playing with, like...
I think that's more cabaret.
If you were doing it this way, honestly, you could.
Is it a stretch thing? Did Chopin have really wide hands and they're pressing the notes down but not making a sound because they can't quite reach it?
No, you're actually only playing one note.
You're playing one note, you're using two keys, you're not making a sound, and it's really noisy.
And it's not for extra resonance to create more noise.
I'm going to separate out don't forget, some concert pianists depress two keys. So I'm going to separate out, like, this technique is not, like, written on the musical staff or anything like that. This is just to make it easier to play the last bit.
And this is specifically key. Oh! If you press down two keys either side, if you've got a black note, you press down two keys either side of the black note, the two white notes, you've got more space to whack it.
Yes, you have. Now, it's not a black note. The ending is a D. So do you want to just change your mental picture a little there, Matt? But you've got it.
So that'll be the C and the E then, either side of it. So the D definitely stands out so you can whack it with your fist or something, rather than just using a single finger.
Correct. This is called safety netting. Yes. Some pianists.
Oh, so you don't accidentally play the wrong note while you're whacking the last note so hard.
Yep. The final bars of Chopin's Prelude Number 24 end with three, I'm quoting here, explosive low Ds, requiring the pianist to lift the arm high and strike the key with maximum force.
Yeah, you don't want to end on a sour note if you're whacking one out in front of an audience.
My God.
Well done, Matt. I appreciated that. Well done.
I'm just going to read my notes. The dramatic motion, while easy musically, increases the risk of clipping one of the adjacent keys. To prevent this, some pianists quietly depress the two neighbouring white keys with their other hand just before the climax, which is called safety netting. Some pianists, Matt, even use their fist to hammer the final few notes. The Lateral book is out now. Just click on the link to get your copy. Yerky is looking at a screen, playing his synthesizer to a 2/4 rhythm. Sections above the keyboard are marked Poles, Group, and Frozen. What is his surprising job? I'll say that again. Yerky is looking at a screen, playing his synthesizer to a 2/4 rhythm. Sections above the keyboard are marked Poles, Group, and Frozen. What is his surprising job?
All I know is, Poles, Group, and Frozen could be exactly how we are right now. I've sort of turned into a beanpole. Matt's trying to assemble his thoughts into a group, and Abby has certainly frozen in place with a sort of horrified expression on her face. So, yeah. 2/4 rhythms. That's quite a simple rhythm, isn't it, Matt?
Yeah, and I know this is
in the group.
We've had 2 questions now that are music related, and I'm quite musical. I do quite a musical thing, and I have no idea for either of them from the off.
Okay.
Synthesizers are normally computer based or electronics based, but Poles, Group, and Frozen aren't related to synthesizers in any way I can think of.
What if it has to do with the North Pole?
Ooh.
This is just dumb, because Frozen, my brain immediately went to Frozen, let it go, let it go. And I was like, wait.
There's group singing.
And Jyrki sounds like a Nordic name or a Finnish name.
It does.
And a 2-foot Poles, Group, and Frozen. Is this... Can't you go on holiday to like a Santa experience?
Yeah, you can.
In Lapland. In Finland or Sweden.
Is this Jyrki? He's like in charge of letting kids through to different sections of the park where there's Santa, and so you got the Poles over in this bit. You got the Frozen children. That's wrong. There's a group of children. I don't know.
2/4 is a march.
Yes.
Boom.
That was the next thing I was going to ask.
Are they marching the children?
No. Okay.
Is that where the elves come from?
They're marching the children into the workhouse to make the toys.
Okay, so
that's where the bad children go.
Good things you have worked out so far. 2/4 is a march. Correct part of the world. The whole children and forced labour thing? No, that's not.
It's one of those Jet2 holidays where you think you're going for a good thing, but you end up working in the...
Nothing beats a Jet2 holiday.
This is well, okay. So Poles, Group, and Frozen. I mean, and a march. So what marches happen in Finland? The only march I've been on recently, and it was weird, was I went to Rotterdam when Santa arrives, or Sinterklaas, right? And that is terrifying because he has all of his elves come off the boat first, because of course they come from this amazing country called Spain, right? So Santa Claus arrives from Spain with all the stuff to give to the kids, and they throw biscuits at you in the street. It's mental, right? They literally just chuck biscuits at your face, and you've got to catch them in bags. But
I'm just imagining Spanish Santa arriving in Rotterdam. Hola, buenos dias.
No, it's not Spanish Santa.
It's very much. So he used to have his elves, which are now they're called Schwarze and in the past Schwarze would be in full blackface because they were obviously, this is pre when everybody was fine with the transatlantic slave trade and everything else, and so that's where it comes from. It's worrying, but now they're not like that, so they don't do that anymore, which is a relief. Well done. Yes, and we're trying to think, is it Netherlands as well? But
it's completely unrelated to that.
Okay, good.
We've already established Finland.
Finland, but they don't have a sort of similar Christmas thing.
No, and you're right, we're up north. It's not like North Pole north, but we're up north.
Does it have to do with the sun and solstices?
The words are Poles, Group, and Frozen.
Poles, Group, Frozen.
Poles is probably going to be the biggest clue there.
So there's 2 poles. There's 2 poles. There's a South Pole as well. So are they doing... Is it like there's a march that happens on the South Pole and the North Pole at the same time, except nobody lives in South Pole, so that...
No, we're literally talking sticks.
And people do live at the South Pole.
Yeah, not right at the South Pole, do they?
Yeah, there's an Arctic research base there.
They're nuts.
Yeah, they don't go out in winter, though.
Okay. Or ever. That is nuts. I didn't realise they were that far south, as it were. Anyway, sorry. Okay.
There's. Oh, you said it was physical poles. I was going to say because there's true north and magnetic north.
No, it's
that's nowhere
physical
near
poles that people are marching with, or something close to marching.
Oh, batons! It's like cheerleading.
Cheerleading is closer, but not that close. This is, in what may be the biggest clue I can give you, a question in sport.
Sports with poles include things like skiing, because you get whipped with them. So, is it to do with cross-country skiing?
It is to do with cross-country skiing, Izzy.
Okay. Right.
Specifically cross-country.
Ice. Frozen is ice rather than snow.
Yep.
And group is people crying because it's the most horrific sport in the world.
Is this someone live scoring the TV coverage of it based on what is currently being shown or what's currently happening?
Yes.
What?
live scoring implies, I think, something a little more musical than what's actually happening. You're nearly there.
Camera changing.
Oh, chanting! You get fans chanting like at football matches.
You might. It's cross-country skiing. That's the last clue here.
Oh, is it to keep the rhythm? Someone
So it's
like
one,
banging
two,
a drum?
one,
yeah.
two.
Nope,
one,
this is just for the TV broadcast.
Sound effects.
Sound effects. Keep
Is
going.
he doing Foley?
Yes, he is, Matt.
Is it because they can't afford microphones?
Yes, it is. You cannot mic up an entire cross-country skiing course.
Oh my god. So he's literally just like making noises and like rustling his own coat and stuff to get...
Well, it's all on a synthesizer. It's all automated sound effects. This is Jyrki Ihalainen, who has artificially enhanced skiing broadcasts for many years. He has an electronic keyboard which produces a soundscape with skis sliding, ski poles hitting the snow, cowbells ringing, dogs barking, and he plays different sounds depending on the snow, the environment, whether they're going uphill, downhill, how far they are from the cameras, and whether we're seeing one skier or a group.
I've not heard of live Foley before, never mind in sport.
I mean, you heard of Foley before because obviously, you know, Ambridge, what's that called?
The Archers.
That long running.
The Archers,
yeah. That they often use it to just emphasise. This is why people, for those who don't know, it's the longest running soap opera ever. It's on Radio 4, and it basically is a load of farmers in the middle of nowhere in, well, Midlands, isn't it? UK. And in order to enhance any dramatic scene, there's usually a sheep giving birth in the background, or somebody like putting their hand in something and squelching, just to give it that sort of like rural je ne sais quoi. And yeah, no, that makes...
And the reason for Foley is if you're on a set recording for audio or audio and video, the one thing you need more than anything else is good quality voice recordings. So generally you won't mic up anything else because that's a lot of effort, and you just concentrate on the mouth sounds and then you add in everything else over the top afterwards. So if you're in a noisy bar, the noisy bar sound that you can hear is normally recorded elsewhere at another time. And it's the same with footsteps and fight noises and...
Yeah, when you see people acting in like clubber scenes, you know, for TV and stuff, you actually just have people talking normally with everybody else miming to no music and pretending to talk to each other.
So I'll ask you to put the last piece of the puzzle together. Why does he have to do this for cross-country skiing? Why doesn't this happen for other ski sports, for generally any sport?
Is it filmed on a helicopter? Or like long-distance cameras, like...
Matt, you've got it. It is really easy to get telephoto images these days. Whether it's from a drone or a helicopter or just a really long lens, it is extremely difficult to get tele-audio sound. It is much easier to get Jyrki in a studio playing a synthesizer to cue in the sound effects. The Lateral book is out now. Just click on the link to get your copy.
Okay, what do I want?
In 1964, Frank built a concrete wall in the Maruia Valley of South Island, New Zealand. It doesn't form a boundary or enclose anything, and 3/4 of it is underground. Why would Frank be disappointed by the wall? Longevity. I'll say that again. In 1964, Frank built a concrete wall in the Maruia Valley of South Island, New Zealand. It doesn't form a boundary or enclose anything, and 3/4 of it is underground. Why would Frank be disappointed by the wall's longevity?
He built a wall, but he wants it to come down.
First thing I thought was just art installation.
I was thinking, I mean, if he's upset by the longevity, is it not that the wall has broken down, but maybe it no longer belongs to him? Or maybe because it's underground, you couldn't say that that's your land?
Yeah, the underground thing is interesting.
Concrete as well.
What's happening under New Zealand? I've never even thought about this. There's probably volcanic activity. Maybe there are weird reservoirs. I don't even know. Maybe there's a secret club down there. I don't.
What's happening under New Zealand is a very good question.
Oh, now I'm imagining a club. Okay.
I'm thinking of all the little animal burrows as they come around. They're doing the club. They're having a little party at the concrete wall.
There's just one very disappointed mole who's been digging that way for one. Sorry, need to remember, do not make jokes like that in my authoritative factual voice. It doesn't work.
Well, Tom Scott said there's a single Kiwi mole.
So I know very little about New Zealand, but I live in a corner of the world where everything underground is a mine. Is there mining in that region of New Zealand?
No, I think Annie was certainly closer with volcanoes. Not that close, but certainly closer.
So not close, but closer, and I will take it. Something like a volcano.
Lava tube?
Mineral degradation. Why did he build 3/4 of it underground anyway? What's the point? What was the point of this wall?
Did he expect it to erode? And then it would all erode away or something?
Erode isn't the right word, but yes, that was kind of the point of it. We are in a remote mountainous setting.
So I'm wondering what it's indicative of, if it signals some kind of change that would be happening underground, like it's a measurement tool in some way.
We're measuring.
Is it to measure like the fertility of the ground, like how good it could be for growing vegetables, or?
No, I'd say you're still closer with volcanoes and things like that. But New Zealand is
tectonic plate boundary in New Zealand.
Yes, there is.
Oh, this is so exciting. Okay. Wow.
It's a timer for measuring when the next earthquake will hit.
That's very close, Charlotte.
Oh, if the wall, maybe it was built at the boundary, and if the wall was to crumble, it would indicate that there was a lot of tectonic movement, which indicates that an earthquake is imminent, or a large one. A scale.
But this guy's disappointed that it still exists. Maybe he just wants the world. He wants the world to be destroyed. And
maybe he wasn't expecting it to be so soon, and then the next day, an earthquake was coming.
You've got most of this. This is Frank Everson, a geophysicist who commissioned the building of a concrete wall across the Alpine Fault, which is the boundary between the Pacific and Australian tectonic plates. You've got that. But you're right, he's a geophysicist. He doesn't want to. He's not trying to bring on an earthquake here. So why is he disappointed that it's still standing?
Was he predicting that an earthquake was going to come within the next year, for example, as a geophysicist? And then a year had passed, and it turned out that it was still standing, so he was wrong in his prediction. But he wanted to prove that he was going to be right.
He was testing a theory, or at least trying to provide data.
Did you say what time frame this was, Tom?
1964.
So this is right when they found out about tectonics. Well,
It's amazing how late the world found out about tectonics. Right?
Yeah, right? Huge earthquakes were happening, and they were like, oh, I wonder why. The Richter, I don't have the exact quote, but the Richter guy from the Richter scale, he has all these really snarky quotes about, like, stop trying to predict when it's going to happen. We, like, barely even know what tectonics are. Just focus on the basics.
Yeah.
But if I had the exact quote, it would be a lot funnier, because it was, I remember it being kind of profane.
You've hit a key point there, Annie, which is that this was the very early days of figuring out that there were tectonic plates, and they moved like this. So why might you build a wall across a fault in 1964?
Did they think that these things were really trucking along, and it's like, oh boy, they actually move so subtly that it's hard to measure?
Oh, so close. Really, really close. I think the key phrase in there, Annie, is move so suddenly. What might he have been trying to figure out?
Is it just as simple as he was trying to figure out what the speed was?
Yes.
Oh.
Yes, he was.
Oh.
The intention of the wall was to shear at that junction, so they can figure out, visibly, obviously, how fast do these plates move. So why would he be disappointed that it's still standing?
Because they move really slowly.
Oh, yeah.
But they still have big effects.
Oh. Well, the trouble is they don't always move really slowly.
Oh, okay. Well, so, I don't know. In my head, they do. That's the stereotype, I guess.
I mean, why do we have earthquakes? What is an earthquake?
Yeah, it's just sudden movement on a fault.
Keep going, Alexis.
Okay. Sudden movement on a fault. One side shifts dramatically compared to the other.
Yep.
Where does the wall come into that?
You know what? I'm gonna give you that. It is. You talked about sudden movements. So this is a wall built across a fault line, designed to measure how much the plates are moving over time, and eventually the wall will shear and it will be obvious and you can measure it. He would be disappointed were he still alive, because that fault has not shifted at all, because that is not how faults move. Faults move very suddenly, causing earthquakes. At some point, yeah, that wall's getting torn down, but it hasn't happened since 1964 because that fault hasn't moved in that direction.
Oh, okay, that makes sense.
This is Frank Everson, a geophysicist, built the wall with the intention to shear it at that junction, but the wall remains resolutely straight. But they did learn that the tectonic plates move in large jumps rather than a slow, gradual creep.
Cool.
The Lateral Producers Club is at lateralcast.com if you would like more lateral, fewer adverts, and to support the show.
When Jack Willems was a test pilot for the Bell P-59 era Comet, he sometimes wore a gorilla mask, a bowler hat, and a cigar. Why? When Jack Willems was a test pilot for the Bell P-59 era Comet, he sometimes wore a gorilla mask, a bowler hat, and a cigar. Why?
This is the first time where we've had a question and all three people were looking down during it. I don't know if that was just thinking and avoiding eye contact or if all three of us are taking notes this time.
I got gorilla hat. No, gorilla mask, bowler hat, and cigar.
I got no notes.
These all cover different areas. Well, how would you use a cigar if you've got a mask on?
Is this a really old plane and there are paparazzi on the tiny runway that it's taking off from?
It's before 1950.
Oh.
Okay.
That's not what I was thinking at all. Okay.
The obvious thing would be it's a practical joke. Mm-hmm. But why a gorilla in a bowler hat with a cigar?
That's it's either very specific or it's very random, and I'm not sure which.
I've been doing a lot of research for some stuff I'm filming at the moment, and I have found that there are so many old references that so worldwide sometimes, or maybe just in one country where everyone knew them for about 5-10 years, and then they just dropped out of pop culture entirely. So I'm wondering if there's some pop culture reference to cigar, bowler hat, gorilla that we don't know anymore.
Gorillas do sometimes smoke. Have you ever seen this?
What?
What?
Yeah, I don't know which great ape it is. Oh, I'm not very good at the primate terminology, so somebody's gonna be listening to this just like, but there's some animal at the Pyongyang Zoo named Azalea who's addicted to smoking. What? And it's really funny, the pictures of it, but then it's also kind of sad. And they'll also like get Coca-Cola. They love all our vices. That's not related to the question.
It's not, but it was wonderful.
Any famous man with a bowler hat taking a cigar? I feel like there must be someone in history.
Winston Churchill, but no, that's just a cigar. It's not a bowler hat. That wasn't his style.
Do you think maybe he tried it out one time just to see if that's him?
Oh, thank you to producer David. Azalea is a female chimpanzee at the Korea Central Zoo.
Oh.
Reportedly able to light her own cigarettes, smoked up to a pack a day.
Right, the pilot was cosplaying Azalea. Sorted, done.
Sold.
Okay, so he was pulling a prank that had practical benefit.
Huh.
Okay.
Oh, and the P-59 was a new type of plane.
Was he trying to get noticed by someone else while flying the plane? Because they're quite ostentatious items.
I'm not gonna say yes or no, but keep thinking about that.
Okay.
Okay.
You said before 1950, right? So that's too early for the jet engine. But
Or is it?
oh, is my hit? Okay, it's okay. So he's an early jet fighter test pilot.
Was this the first jet engine plane?
Also, I assumed fighter. Like this has to be a wartime or a.
Ooh.
Is it a Second World War thing then?
Yes.
Right.
We are in the depths.
Alright, that's going to be it for the stream. Good luck, fun, thanks for watching.